Start recording.
Okay.
I guess I can start screen sharing.
Let's share the slides or show. Yeah. Either way, doesn't matter.
Sure. Let me do this here. Just do something. Can you guys see? Okay.
Oh, looks amazing.
Yeah, that's the slide. That's the one slide we presented. We prepared.
Yeah, this is the whole presentation.
Mandelbrot.
Just behold. Yeah, this is from Mandelbrot's kind of notebooks when they used to do this very crappy computing powers. Yeah, but so the idea for today, I think we have like, we're not like dividing the presentation into who presents what. We're just gonna wing it. But
we'll see how it goes.
Yeah, we'll see how that goes. But the idea is pretty much just to give you, like, we prepared first just some kind of recapitulating slides on topics that were under discussion in the last couple of meetings, following that suggestion that we agreed on of trying to connect presentations to previous presentations. So we just had a couple of slides on ideas and questions that were raised recently that this presentation can help with. Then there is kind of a very brief history, kind of following Nottale's own presentation.
Not as brief anymore, but
yeah,
we'll try to go through it pretty quick.
Yeah, the resolution of the history there is a finer-grained, a mid-grained history of relativity. Then we try to debate, after going through it, a more kind of philosophical take on what the relativity principle is, what it means as a method, because that's something that Nottale tries to separate. Relativity as a theory or a set of theories, and relativity as a philosophical principle that kind of helps out coming up with theories. So in itself, it's already interesting for us, I think. Then the way that he addresses the crisis in contemporary physics and the sort of symptomatic points that he localizes, like locates and says, this is where we should intervene to change something. And then points 4 and 5. 4 is pretty much going over very quickly some of his ideas of how to kind of increment. In fact, it's not even a
very rough way.
Yeah, very roughly. And we have a lot of quotes by him. So it's more for us to have a discussion and so on. And then the 5th point is just trying to kind of extract some ideas that might be useful for us in different ways and things like this. I think that before we talk about Nottale, it's good just to go back to some ideas we raised, especially in the last 2 meetings, which were kind of a development on top of the primer, but already trying to connect with other stuff we've been doing. So one of the things we did at the beginning of last meeting was to define a couple of ideas of how to define what is a scale and what is a resolution based on different approaches we already mentioned until today, right? So we divided them.
Yeah.
I would say that
in like 3 categories. Yeah.
Yeah, exactly. I think you can divide it. So for example, I think this is the first one, which is a more common, not common sense, but it's an easier one to understand, or it's more intuitive perhaps. It's nice to start talking, but it's easy to show that it has some limits. So what we call the language approach to scaling, which is here resolutions are operational concepts that move you from one domain of predication to another scale of analysis. So for example, if you are talking about trees and you have like predicates of the type pieces of wood, it's tall, it's blue, it's whatever, the tree, it kind of, the domain of predicates, right? That predicate is connected to other ways of describing things that allow you to describe stuff around the tree in some ways. Other tall and small objects, or things made of wood, things that are not made of wood, trees that are crooked and ones which are not. I don't know. It defines some space that you can predicate things upon. But you can define resolutions as a way to operate a change in this domain. So now rather than describe stuff in terms of wood and some properties of wood and trees and so on, you might be talking about molecules, which are part of the tree in a way, but the domain of predicates that come together with talking about molecules, right? The other predicates around it are now different. You're talking about molecular structures, you're talking about the geometry of these structures, you're differentiating things in different ways. The world doesn't look the same, right?
Yeah, one way you can put the language approach is kind of as like a naive, like mereological account of scale, right? By like parts and the ways that like sets of parts divide up, right?
Yeah, something like this. And why are we separating this from the other ones? I would say we can take this tree as a second set, and this two as the last ones. Why is this separate? Because this language approach, it doesn't have a sort of immanent description of the limits of this operation. So that, for example, you can move from a description at which you can affect things. For example, when I have a domain of predication that talks about trees in terms of their forms as trees, what they're made of, whatever, I can throw a branch that was on the floor at the tree. I can make differences that are captured by that way of predicating the tree. But I cannot make a difference of the tree that is captured molecularly. So if something about the molecules of the tree slightly change, there is nothing to do. It doesn't make a difference in that world. So it becomes a metaphorical description. You can move continuously from, let's say, the reference to something in that domain to the metaphor, where it's as if you're talking about the molecules of the tree, but you're not really engaging in any molecular way with the tree, right? It doesn't add any information to that world. So you need something else to start talking about resolutions in such a way that when they change, you could call it like an effective resolution change and not a metaphorical resolution change, right? For example, you can make a metaphorical one by saying, well, we're here on planet Earth, but we're also in the universe. We're part of the universe. But you know that in a way, that's a metaphorical way of talking about the universe because you're not really engaging with the universe in any way. None of the things you're doing are captured by differences discussed at the cosmological level, for example, right? So something is missing in that description. So this second set of descriptions, it's attempts.
I would say,
yeah, sure,
yeah.
sorry.
One way to think of them is I don't think you want to necessarily think of these three descriptions as distinct or necessarily even different per se. There's sort of three different approaches that where we are now, I would say we don't know completely how they necessarily tied together or which one is the most relevant for what we're interested in, but they all sort of lead us in the same direction, right?
Yeah.
So the first one is this idea that Dennis mentioned before about these resolutions as endo-functors, so functors from a category to itself that you can think of as like scaling that space, right? And so if you like take a set of parts and you apply the endo-functor to it, then it will bring the parts that are kind of above it that unify all of these separate sets, is at least how I'm understanding it.
Yeah, and I think that the crucial part there being the fact that it needs to also hold some added properties, right? So you might imagine ways of scaling something, of changing the resolution, but not all of those ways will also guarantee some other arrows that are important for that world, right? So these other arrows, right, these certain commutative properties, they give meaning to what they constrain which resolutions exist in that world, right? So it's no longer a matter of changing scales in the sense of your conceptual language. It's a matter of how the structure of the world allows you to change between certain scales, but not all scales, right?
Yeah, it gives sort of like the logic of what is preserved. I guess this is like the way you're thinking, the logic of what is preserved under scale transformations and how. Something like that. The second idea, which
Dennis wants to add something there, perhaps.
Oh, yeah.
Oh,
has anything specific.
I have a problem, even though I really want to make the endo functor thing work. The problem with it is like, we don't have an easy way, at least with our knowledge, of talking about like convergence and divergence when applying the endo functor. It just seems like you just keep applying it, right? And then you just scale up and down in a category without any costs.
Yeah.
This is why I think that I would actually make a little asterisk here. Because it's not that the complete definition. Dennis wrote this up on point 2.5 of the primer. But I think that what makes it a consistent, the idea of effective resolution, is actually when you bind this together with what happens after point 9 with like capitalist productive units and so on. Because then you see something like this. You have money, it needs to valorize, right, into more money. Here you have this box where some scalar process can happen, right? And this is the diagram. Like, this is the stuff that actually constrains this arrow, right? Like at 2.5, you only have this in a way, or even a more general idea, right? So we only get to see that you're adding some diagram that constrains what is allowed when you look at it in the productive process, because then it's not about any any resolution that is interesting. It's precisely those resolutions that will lead to the valorization diagram we had and so on, right? So I agree that in the point 2.5 there, it's still very general. It's very much like the language approach in a way, right? Perhaps just written in a formal way that is more kind of, you can integrate it better with other restrictions, right?
Yeah. I guess to go on to the second, this is something I kind of propose and have been thinking about. And I think it does sort of fit well with in our specific like a multi-layered transcendental approach, as resolutions as sort of taking, you think of taking like a horizontal layer of objects and then generating them as a filter over, if we imagine the transcendental, that it's a sub-object classifier of our space. So it shows how objects are divided into sub-objects. So you take a bunch of these and then you generate a filter over them, and that completes this set as like some sort of rudimentary resolution or scale, right? So it depends on the completeness of the objects you choose at first, but then when you group them together, you can sort of jump up to a higher scale. And similar to in the picture that Gabriel had above, or actually from specifically the picture from last week, where there is like, you saw the layers of the different productive processes from at the level of labor to at the level of the production process to capital and so on. Each time you sort of gather together these objects of the same scale, if you don't necessarily have a way to compare scales between different incomparable objects, when you gather them together, you can get a whole, which you then...
Would it be okay, I mean, just to make it more intuitive for people, to imagine, going back to that intuitive, more mereological thing, imagining you have something like, right, like the tree, you can talk about its like pieces here, right, another piece, then you have like very below this level of description, you have like the molecular description, right? And it would be something like taking this covering.
Yeah, exactly. So this covering down here, each one of these will complete up to something above. So like these, I don't know, these molecules on the left will complete to this first part of the tree. The molecules on the right will complete to the second part of the tree. And these are like the shifts in the scales. But each scale can have different resolutions within it. I think we'll talk about this on the next slide, which is an important point about how,
but I wanted to talk about the same diagram. I wanted to ask that in the second definition, each of these layers are a category, or all of this is a category?
Yeah, no, I'm imagining this. I mean, it's sort of a little bit of an ad hoc definition, but it's, I'm imagining this as everything living within the subobject classifier, which is right in Badiou, the transcendental, which it shows how your space is divided into predicates.
Yeah, so
this would be like a subsection of it. So it's ways to slice it kind of horizontally in ways that are locally complete in like different sections, I suppose.
One thing to add, one piece of this is that Grothendieck found a way to interpret categories as spaces, right? And if you think of the terminal object is kind of like would be like the top object here. And you can interpret basically the lattice structure onto all sub-objects of one, right? So like zero is the bottom, one is the top, and then all the objects of your category are here. So what you're saying is the resolution would be like the layers, the levels of this
something
space, right?
like that. But the issue is that, remember when you have subsets that don't intersect at all, that have no like interaction with one another, they're not necessarily comparable to one another. So you don't necessarily always know how to match up like scale levels on different like incomparable, I guess,
branches,
chains up and down, or ranges. So it's sort of a working definition.
What I think
not
that
really
this
rigorous
definition, yet. But what I think this definition has that the language one doesn't have, and the categorical one that we currently use in the primer doesn't have as a clear explicit thing, is that you first have the transcendental structure, and then you have these filters on it. So it's reliant on the structure of the world, right? So it has some constraints, given the constraints of the world. It's not like you can just go anywhere zooming in, right? There will be a time where there is no information there because that world doesn't really differentiate those things, right? But just so we don't use too much time here. So the third one is this type theoretical one, which is kind of, from what I understand, a way of binding these two, again, with a more predicative approach, right? Dennis was also added this to the primer in the last version.
I suspect in homotopy type theory it would have a lot of deep connections, but
yeah, I imagine so. But again, just to go very quickly over it, again, it ties together this sort of constraints on relations, this sort of way of recovering or repartitioning the objects in your category with this connection between the spatial thing, right, of partitioning and synthesizing again, but with the predicates. So when you talk about things getting indistinguished, so you have like something here and something here, and both of these are mapped onto the same type here, right? This means that from the perspective of this, these two things are indistinguishable, right? They count as the same type. So they kind of they become one bit, right, of some predicate rather than differentiated on their own, right? With the added benefit of, if you work within these ideas, they connect directly to your description of the structure of the world. So there is an immanent connection between how a world is structured and how you can partition it into parts that are meaningful in that world. So it kind of has a built-in kind of distinction between redescribing a world in a way that is not meaningful in that world, right? Which would be this metaphorical way of doing it, or actually having an effective resolution change that is still kept inside the world, right?
And another thing, when I guess bring this to questions we're interested in, it's important to keep in mind that in when we talk about scale in the context of physics, everything still, like the laws of physics still have to apply the same everywhere. But that's not necessarily the case in, like, for example, things in the primer or in other similar like scale spaces.
Yeah, I think that this is
so there's a certain continuity difference, and it's important to keep in mind what baggage is coming kind of like from physics.
Yeah, I think this is actually a big discussion to have at the end of today's meeting, because there is a very strong, I mean, 99% of the complication of the presentation today comes from the fact that this guy is not only defining a concept of scale, but one that actually holds with, like, keeping the laws of physics valid, right, across this scale. So it's a very specific sense in which this works. And of course, a lot of it doesn't really kind of, cannot be transported out of the theory. A lot of it functions as a sort of inspiration to think about these things in more detail. But I mean, for example, this thing that Yasha just said about, yeah, you want to change resolutions, but they cannot really break with the basic laws at stake. It's actually something that in the primer we're trying to hold, the idea that the resolutions that are really relevant for commodities, they might change the structure, they might make you look at, let's say, prices in very different ways, depending on how the price structure is kind of synthesized, but it still abides to some basic laws of the commodity world, right? So we're still trying to connect this idea of predicating and abiding to some immanent logic of a space, even if you want to show that there is some room to change there, right? And I think that,
sorry, go ahead, finish your sentence.
No, I was going to say that I think that today what we're going to do is actually help out with this third point here. The last two meetings, Dennis brought this up. He got an example from a Julia set with this idea that you, for example, you can start with like at iteration 1, a line, then at iteration 2, you add like this dent. At iteration 2, you add like this, right? And so on. So you actually add information, like the length of this is smaller than the length of this, which is smaller than the length of this, and so on. You're adding information the more you iterate, right? So we made the, again, just a starting connection between the resolution being something like this iterational limit, where you stop, on something like this recursive function, like a recursive function of the complex plane, right? So it's nice because this definition has something which the others don't, and which we're going to be exploring today a lot, which is a connection between the resolution and a sort of cost, right? Why are Julia sets or these fractals calculated up to some iteration? You can find on YouTube like 200,000 iterations, but it's always a finite number, right? Because of limits to computing power and things like this. So, and to physics. So you get a connection between this element that we were seeing a lot when talking about Bogdanov, about this sort of cost that kind of grounds this iteration of the function on some limit that comes with the world, right? It connects the idea of resolution to that limit, right? Or better, connects the idea of limits to some instrumental limit. Which is something that today I think we're going to be exploring a lot more, because that's pretty much the core of Nottale's insight, I think.
Yeah, basically his entire insight is all about the fractal geometry approach, right?
Yeah.
So I mean, the really important thing here is the non-differentiable paths. Is that we'll talk about. He gives up the hypothesis of differentiability, which basically means that. Or at least his conclusion is that means that all scales, there's going to be structure which is not reducible to the structure at just lower scales.
I think also, I mean, I was really surprised by when preparing for this. I mean, when I read Nottale's book, like the one that he wrote just for kind of public dissemination of the ideas, it seemed like it was I didn't feel like a big change in my intuition of these ideas, just felt like it was corroborating. But once you get to a bit more details of what he's trying to do with his other books and stuff, it's actually, I mean, what interests him in fractal geometry is nothing like you would expect in terms of what we see people talking about fractals. Usually it's very specific, and it's, and you actually need to, I felt like I had to shed off some intuitive ideas I had about how to think about scales and resolutions and so on to actually meet his approach. So I think that there is also something to this, which is not simply, let's say, adding some information to the previous definitions we had, like giving some concrete example or something. But I think it also gives a slightly different intuition of what these things mean, you know? Mm-hmm. So I think that's also important. I added another slide here with just to show why these are very technical problems, right? I added another slide with a sort of conceptual distinction, which I think is a distinction that we want to make at some point, right?
And it's a good way to think of this, how Nottale's work kind of divides space up, right?
Yeah. So what I thought of, like the way that I thought of dividing things, just because I think we want to be able to speak rigorously about how these things are different, right? Is the difference between, just first to start with just having an idea of attributes, because it's clear that given some object or objects from a category, you can talk about them, you can predicate on them in different ways already, right? As I was saying, like if you have a tree in a field, you can talk about the tree in infinite ways. But most of those ways, or a lot of those ways, don't require you to change anything else. They're all compatible with that world, right? So if I talk about a tree being tall, I don't need to commit to describing anything else in a different way because of that. That's fine. Or if I talk about the tree being ugly, or because the tree being like this tree and not like that other tree, like I can actually do a lot of exploration of this predicate space without really changing anything about the world, right? So we don't want to simply identify resolutions with defining some predicate space. It has more than that. It's not only an analytic principle of how you're going to divide your space, right? So resolution adds a syntactic principle, right? It's determination of something like a unit or some basic predicates that also come with a way of measuring the world. And if you take measure to be something that captures information in some way and fixates it, you can think about it and allows you to kind of operate on those measures. It's like you're adding some choice of attributes to something syntactic about it, right? So there is a chain, there is a specific difference between moving from...
Synthetic or syntactic?
In the sense of synthesis.
No, I know, but I was thinking about probably because of the structure, the language of a structure, only a certain type of a structure is allowed here.
Yeah, you could probably translate this in terms of changing like the syntax of how things are operating. It's not only, right? I mean, it's not simply saying like I have the tree is X and then I change this X, right? Different attributes, it's tall, it's big, it's whatever. But it's something that once you plug it there, right? Even the way of talking about, for example, it might no longer be a tree, right? For example,
it reminds me of what Badiou says in Mark and Lac in terms of different levels of operations. I mean, we have signs. These signs are like attributes. And then we have laws of combining these signs together, right? But then some combinations are not allowed, or are irrelevant, or meaningless, right? The fact that the grammar that says which combination of signs is relevant and which is not is like a syntax.
Yeah, I think
Yeah,
maybe I'm thinking of a wrong paradigm, but
I think it's a good analogy with the idea that it brings about some operational change, right? Mm-hmm. It's not just some variable you change for another predicate and that's fine. It's, for example, it's a difference between saying the attribute idea is like saying the tree is tall, the tree is small. And the resolution would be the tree is part of the forest. Now the tree is no longer the whole you predicate. It's actually taking its predicates from the forest that you're, now that's the object that receives the predicate. So it changes something on the structure, right? So it has
the important thing about, I think, the resolution is different resolutions don't necessarily make a difference, right? They can, but they don't necessarily. So you can have like a whole continuum of resolutions within a certain confinement that are completely consistent with one another.
Yeah, I think that's something we're going to see.
That is kind of what happens in this.
Yeah, we're going to see a lot of that. So that's why we also add the difference between a resolution and a sort of qualitative limit of resolutions, because you might have a way of redescribing things that do change operation the way you're describing them. For example, if you're talking about a car or parts of a car, that actually changes a lot. Like, consider the parts as something in themselves and not just components in the car. That might change the way you view it, but it might not really change the world that much. Even it's within a resolutive range that still abides to the same world, because everything that composes with the auto parts kind of also composes with the car. So even though it's a change that does have added information, it might bring something about that wasn't there before. You can speak about the car parts in a new way. It doesn't really get to change much about the world, right?
And I'll say the resolution range is kind of like what this lattice theory definition of scale is trying to get at.
Yeah, that's why it seems to me like
as like the definition of like a single scale, right?
Yeah, the ranges that fall into the So
the range is a partially ordered set, or is it?
Yeah.
One set of layers, or?
It can be. It really depends. I mean, in the case of Nottale, the resolution range would just be a range of different like resolutions of your measurement. So it'd be, and the resolution of the measurement is basically just the error of the measurement. It's what that little error bar is.
So for example, you can
the
talk
minimum
about
error bar of your measurement. But we'll get into that.
Yeah, we'll get into that. Like you can talk about, I don't know, you can meaningfully talk about cars and reduce or increase your error margin. If you talk about the size of the car in, I don't know, centimeters and meters, they're still like capturing something. But when you get to kilometers, it's not really a matter of the error range. It's just not meaningful to talk about the size of a car in kilometers, right? Or in very, very small measurements. So you went beyond like this range within which you were kind of messing with what's the error margin and what's the meaningful quantity, right? And it's a continuum. So there is a certain range where everything kind of converges and kind of keeps the cohesion of that description.
And the edges of it can also be fuzzy. It doesn't have to be like a strict line, as we'll see.
Yeah. So all of this is to say that we want to move from attributes to resolution by adding some syntactic consequences. We want to talk about resolution ranges because they seem to be kind of allow for some loose movement, which might change operations a bit, but they're still contained by something. Something sets up the limit, and we're going to see where we can call this a sort of instrumental condition, right? So for example, your ruler can measure meters, centimeters, for example, millimeters. Those can actually do give you some difference depending on what you're measuring. That's a relevant thing. You can capture that difference as a margin of error, right? But that range from millimeters to centimeters, perhaps meters, it's actually constrained by the instruments that actually can make a difference, right? Or capture some difference in that world. So we only get to scale change. So you see it's kind of building up. Once the change in this atomic resolution, right, this kind of predicate resolution leads to a material synthesis of the world that does not preserve the minimal and maximal of the origin world. Right? So
it's like the different equivalence classes of resolution ranges, sort of.
Yeah, you would take
when you jump between them.
Yeah, you jump out of this sort of inner range to the point that the synthesis of the world, the way that the parts of the world be mended together through the whole transcendental functor funny game of Badiou, actually gives you a different world, right? So that's why you would say that, for example, the world of classical mechanical physics is not the same world as a quantum world, right? So the scale change actually, if it truly constitutes a different synthesis of the world, it constitutes a different world, right? So there would be a very important relation between the theory of worlds and the theory of scaling. Right? We will see that actually this is not a constant, because there are worlds, for example, the religious world, where all ranges actually converge. Because, for example, everything is made by God. So God is the maximal and the minimal are theologically defined. There's nothing you can change that doesn't get you to that same world, right? To the same kind of cosmos in the kind of classic sense. So there's nothing necessary about this change leading to a changing world. It really depends on the origin world, on its minimal and its maximal. It's not like a substantial difference. Worlds are not the same as scales, but given a world, we can see a scale change in some way, right? So you see that there is a correlation between resolutions, the structure of the world, and what will count as a scale change or a qualitative scalar change in that world. And I think that, and the last point is that we want to distinguish.
It becomes like a way of moving between worlds, right?
Yeah, it can be a way of moving between worlds. Yeah. I mean, it makes sense because, for example, a lot of what we did in the primer is to show that capital is interested, we could translate it in saying something like, under the instrumental conditions of production, capital is interested in exploring the resolution ranges without like leading to a scale change that is not actually within its own capitalist range, right? And not to forget, like the minimum, the maximal of the world doesn't mean it's like a static thing. You can actually get the world to adjust to it under some conditions, right? But it's important to separate this idea of scale change from the idea of layer change, right? For example, when we talk in the primer about there being multiple layers, form logics of exchange happening at the same time, it's not really the same thing as, for example, if I have some object and I move it to a different resolution, and the world in which this new resolution is in is different from this world, right? It's more like I have, for example, I think it's akin to saying something like, imagine you have something like this, and you're filtering this world, for example, a logic that counts things 2 by 2. And then you have a different logic that counts things 3 by 3. And a different logic that counts things like in four elements at a time. They might lead to different properties, right? But they don't really get in the way of each other, right? So that's why we say here it's a change in the atomic resolution, right? From 1 to 2 to 3 that leads to a material synthesis of the world that adds information that is not accessible just by talking about the same thing, the same set of elements in the same way or in different ways. You're actually taking you're making different parts of it, right? With 1, 2, or 3 elements. But these different parts and this added information does not contradict this origin world. So you can actually have all of them coexisting at the same time. So
this is, I think you can think of it more like a lateral shift rather than a vertical one.
Yeah, I agree, yeah.
You slice up your space in a different way, but it might not, that method of slicing might not contradict the previous one.
Yeah, exactly. And I think that it's almost like you took this attribute idea some other direction, right? Because you do get, let's say, predicates that build up different parts of the world, but this predicative topology, they actually have the property of adding information, but not contradicting each other. So they add up to each other. They can depend on each other and so on. Whereas this direction we're taking here, this new description does not converge and does not add up to the other. They cannot combine them, right? They are in conflict in some way. They don't describe the same space, and you cannot add them both up and have effects on both at the same time, right? So it's a different thing. So I think it's important to also make this distinction here, so we don't think they're the same thing.
Mm-hmm. So I have a question.
Yeah.
Is it fair to say that this is the syntax, or these are the set of definitions that allow us to move from one word to another?
Maybe not all of them, but it is scale change, I think specifically is.
But what does a scale change mean? I guess we have to go back to the definition. But let's say in Badiou's language, you have a word that is primarily defined by transcendental. Within that world, or at least I don't recall, there is a discussion of scale within that world. Unless you introduce a new transcendental, which I believe what primer does, right?
Well, the thing is, even in Badiou's formalism, it's never like just one transcendental that is there forever and is like God. It is whenever you take a sub-object, you get another, if it's complete, if you complete it all the way down, you get another transcendental, but just for that subset, right? So that's already a way to, I mean,
not necessarily a subset of the world is a world itself. I mean,
yeah, not all subsets.
Yeah, it doesn't have to be every
form
subset.
A new world.
Yeah.
So the world is strictly defined by having a transcendental, which defines the internal operations of that world, right? It seems to me, if Nottale, so what I read from Nottale, which I couldn't finish all the assigned chapters, but it's a language. I don't know whether this is the language, like a frame of reference. Mm-hmm. He says that the principle of relativity, I guess we will talk about this. The principle of relativity
in a few slides,
is actually the fundamental principle of all science, because without the principle of relativity, we cannot even say that science has laws or nature has laws. Because if you look at the laws of nature, there are laws of nature that are at the face of them, they are contradictory with each other. Or at best, they are irrelevant to each other. So how could, under the assumption that there is one world, how could there be multiple laws and one world? The only way that we can make sense of this and then finally come to terms with, or be able to say that nature has laws, is to say that there is a principle of relativity in place where when we talk about laws of nature, we are strictly talking about a frame of reference. Within that frame of reference, we talk about those laws. Now, when we change the frame of reference, we talk about different laws. If we enlarge the frame of reference, in the case of physics, he has many examples like Copernican and then Galilean and then the Newtonian and then general theory of relativity. We are enlarging, it's like enlarging so the scale in this case makes sense because we are all talking about the same world, but in different scales. But I think it has something subtly a little bit, so far, I completely understand this in the language of Badiou's transcendental. But I think it has something subtle in it that I don't think was a concern for Badiou. And that is the movement between one world to the other world. Because the change of frame of reference is not only change of the frame of reference between Copernican and Galilean, or how we understand the concept of motion, for example, or how celestial bodies and terrestrial bodies are related or connected to each other. These are all, to your point, Yasha, in one vertical movement.
Mm-hmm.
Whereas the frame of reference actually changes from horizontally as well. Like you go from physics, you go to, say, some other principle altogether, like biology, or even to anthropology. I mean, these scale frames of reference can talk about different worlds altogether, not just moving vertically within the same world. So
yeah,
I don't know whether I'm saying something that is relevant, because this is.
I think we can give a bit more meat to that discussion.
Yeah, well,
with Nottale, because I think he gives you more clear examples of how to think about this thing.
Yeah. Mm-hmm. I mean, Nottale discussion is a lot simpler than what you guys are doing here. This is a lot more abstract than what he's saying.
I think it's on a first reading. Maybe I would agree, but I think it's deeper than it gives it credit for. But we'll get into it.
Yeah, let's try to continue.
Yeah.
So I mean, I'm just adding this. This is way beyond the scope of this presentation, but this is again, these are just the underlying things we've been discussing for last months, right?
Mm-hmm.
Different ways of defining what we call resolutions. The concepts we want to kind of separate and distinguish rigorously. So these are bigger goals than the goal of this presentation, but it seeks to contribute to this ongoing discussion. So I think that's the big point, right?
Mm-hmm.
So I think this, just to start off going into the actual matter of the stuff, the book that we thought we had as a basis for the discussion is this one here. It's the most recent one, which is a more popular account of what he does in his theory. But this one is actually the kind of branched out description of what he's doing. So he kind of makes it popular with this one. And this one that he published a long time before is a kind of rehearsal.
The genesis.
Yeah, it gives you like, okay, this is the stuff I'm working on. But it's interesting for us, and people who get interested in this presentation, I suggest look up this book as well, because he was trying out many approaches in this one. So he makes direct formal connections to things that we are studying. So you will find some basic discussion of things that connect more clearly with set theory and things like this in the first one, right? This is also important because he was working on this at the time that Badiou was publishing Logics of Worlds, right? Which came in between the two. And they were friends at the time. So
are they not anymore?
Yeah, no, but they were already friends at the time. So what's the status today? I asked Badiou about Nottale a couple of years ago. Actually, one of the last times I was with, I think the last time I was with Reza, right, in Princeton. I asked Badiou a question about it, and he says, yeah, that's important. I'd love to write about it. And then he just like went into another question. I remember he thought my question was actually coming from Dennis, because Dennis clearly looked more bright. So he said, of course, this is Dennis' question. So he looked at Dennis while he was answering. And I was the Latin American guy, so he thought the political question that Dennis asked was my question. But so it's interesting to see, because I think we can argue that some part of this theory is actually built into the mechanisms of Logics of Worlds. Like Logics of Worlds is already the logical atomism of Logics of Worlds. And some of the sort of pseudo-idealism of saying that the transcendental is connected with the logic, and how can it be that the transcendental is immanent and so on. Actually, you get a very concrete example of this with a theory of sort of experimental connection, the connection between experiments and resolutions, and the kind of collapse of the system of reference for Nottale, which is not an idealist interpretation of measurement. The observer creates the world. It's actually quite materialist.
Very materialist.
Yeah.
Mm-hmm.
So it's I think it's a really good example of some details of Logics of Worlds are at stake here as well. So this is the fella, this this Zen-looking person. He's actually a Buddhist, in fact. I don't think we need to go through all the details, but I think it's worth mentioning that Nottale, from what we've read, Nottale is actually in a weird place because he's very well established as a physicist of relativity. Like, he contributed to relativity theory with well-established and kind of celebrated stuff on gravitational lenses on one side, and also with new axiomatic treatments of special relativity, showing you can derive special relativity with a lot of with fewer kind of assumptions, and also a big proponent of decoupling the constant from the speed of light, showing that it's very important not to read the speed of light as being a finite constant as a kind of key to understanding things. So he's well established in that field, but he developed scale relativity kind of as a separate project.
Early 90s.
Early 90s thing. And it sits in a weird marginal place in the physics community because it's not like it's considered like a crackpot theory, but it's also not like the theory everyone is getting funding to do or anything like this. It's just kind of sitting there. But while it's been sitting there, it's also been proving itself to have interesting results. A lot of kind of more precise measurements of certain phenomena, predicting the existence of some exoplanets where a sort of periodical fractal structure of the solar system should be. There should be something there, and there was. And interesting predictions. I didn't list the predictions, but quite a long list of stuff, especially in the last couple of 2 or 3 years. But it's still kind of a fringe theory, and there is
a long list of very specific things, like very weirdly specific observations in very different fields.
Yeah.
So it's difficult to like give it like full experimental validity.
Yeah, it's not like the guy discovered predicted a particle and then there it was.
Yeah, but it's also, even though it's maybe not as funded as at least string theory once was, it does seem like it at least has more predictive power.
Yeah.
And
not
I think that it's as complete, but.
Yeah, I think that, but it's interesting to see that, I mean, a lot of the comments, especially there's two sociologists who study the reception of the theory, and they say that it's not a controversial theory. It's not like it's being debunked or anything. It sits in a weird place because it seeks to reframe a lot of already existing ideas and say you should be thinking about them geometrically rather than probabilistically, but it wants to integrate a lot of already existing stuff. So that's not usually a good motivation for people to change their way of working. And second, it goes against the flow of how things are actually being developed today. So that's one of the reasons. I also think by reading him and talking to my dad, who is a physicist, my dad was bothered by the sort of exaggerated elegance of the proposal. He said, it doesn't have the nitty-gritty look of people who make contributions to physics. It looks like he captures the idea, like he only read the last one, right? The popular one. He says, but it seems like he takes the idea, he gets the idea of relativity, and then he says by analogy that it should also apply in this domain. So as if he's enamored by the idea too much, right? I have the impression that the fact that the idea fits so nicely in the continuation of sort of Einsteinian spirit or relativity spirit makes it so that sometimes he is kind of too enchanted by showing the continuity, right? And that can give kind of the feel that there is something too vague or too philosophical about it, perhaps. But
because it also starts from a very simple set of premises.
Yeah.
But in the same way that general relativity does.
So I have the impression that the presentation of it might not be in the language of the working physician, but at the same time, the guy is a physicist, and he is and it seems to me that people who actually engage with it usually get pretty excited about it. But anyway, so just to say, it's a fringe thing or marginal thing, but not like a crackpot thing that we present. I think it's weird because, and kind of interesting that most of the papers that he wrote, with the exception of the core papers, which establish the theory, predict things, and get results and so on, a lot of it is in other fields like geography, biology, economics, things like this. He has most people who get excited about his theory are coming from outside of physics and seem to be interested in the kind of general framework of scale dependence and scale relativity for fields where this is already because I think they are lighter fields. They don't drag that much energy to change, right? Mm-hmm. They're not so basal like geography, for example. To have a shift in paradigm in geography just requires like 10,000 people. Yeah. Like, it doesn't take that much. So these fields that are lighter seem to be interested in it and willing to like imagine a big shift in perspective because of it, right? So just to give a kind of general context. So with this said,
can I jump in? Just a small note. You know that thing that the big news in physics from like this week about the muon? Yeah, apparently Nottale had a paper about it from
did he?
Years ago.
Actually did that.
Yeah.
Does it agree with the observation at all or no?
So
tentative observation.
I'm not sure. It's like way above what I understand. But
corrections to the muon's anomalous magnetic moment. That's exactly what. Yeah. That's exactly what they measured.
Yeah. Apparently, so even before this recent thing, there was a 3.7 sigma discrepancy, and this paper shows how using scale relativistic stuff, you can correct it down to a 1 sigma difference. So it like matches more closely to the experimental data. But the recent thing that happened increased it to like a 4.2 times.
Yeah, 4.2 sigma. But this is talking about the sigma discrepancy, so it's different.
Really? Okay. But it was 3.7.
Yeah, because he's saying that he's going from 3.7 to 1.
Yeah.
With a scale relativistic correction. I mean, if this is just because it's saying 3.7 sigma discrepancy. When you say in like particle physics, when they say like whatever sigma, it is the amount of differences from the standard deviation, right? Yeah. So here the higher sigma is better. So I think this is would be a lower discrepancy is what you're saying. I'm not sure. Yeah, I saw this earlier.
Yeah, this was revised it was submitted last year, but this paper was revised like 3 weeks ago.
Okay. So maybe he has something to say about it.
Yeah, he might incorporate it, I'm not sure. Yeah. I guess he's happy about it, otherwise he wouldn't update it, I guess.
Maybe. We'll have to look. I'll have to look closer to that. But he talks about it at the end. The muon GT Fermi Lab experiment aiming to reproduce. So I think at the end, he seems like he's saying that they're gonna calculate it again or something. Complete a new theoretical calculation of the muon AMM in the, I don't know, SSR, scale relativity framework, right? I don't know what the first S is.
Yeah, so this might be one of those random things that confirms
potentially
like one piece of experimental evidence towards scale relativity.
So that said, we have like a really, not that quick, but I think perhaps we should make it a bit quicker, right?
Yeah, let's try to, hopefully people have a little bit of a cursory knowledge already, and we'll try to go through like the main points. I'm sorry, we have dirt bikers going past my window. Nottale sort of starts the history of relativity with Copernicus, with this move of decentering the Earth, which, I mean, pre-Copernicus, right, the Earth is always the center of everything. So then there's one universal reference system and you never have to change anything. So starting from Copernicus and then with Kepler noticing that the planets aren't just orbiting in the circle, but they're sort of orbiting in the ellipses around one another, and not that the sun is just purely in the center. So, I mean, the consequence really taken to the extreme is that there's no absolute center of the universe. So it's in this context that Galileo established what's called Galilean Relativity, which is the statement that the laws of physics should be invariant under translations of reference frames. So if I stand here, then I move 5 feet over to the right, or I move to the other side of the universe, the laws of physics should not change regardless of where I am. That's the basic idea. But the really important note, and this is something that holds up until Einstein with general relativity, is that all the reference frames have to be inertial, which means that they're non-accelerating. So a reference frame can only be someone moving under a constant velocity. But already with this approach, you can now think of, like Galileo already had, he said something I think we were discussing yesterday, like motion is like nothing, because I mean, if someone's passing you, but or two people are moving, from each other's perspective, they aren't moving. If there's a third perspective seeing both of those people moving, right? So changes of reference frames should preserve.
Yeah, and I think that it's worth mentioning, like, something at this point when it's simpler, right? That this, I think, sets up very clearly the challenge of why relativistic approach to things is actually complicated. Because let's say you're standing still, somebody moves, right? And well, you will have some equation to describe their movement. Then you're moving together with a person, and the comparison between the two of you, you're actually standing still. Now you want
equation is 0, yeah.
Yeah. Now you want these two descriptions to be kept. You want the equation to be general enough that the transformation between those two standpoints are already contained in the general version, right? So this is the weird thing, right? I think it's nice for us to talk about this just because it gives a clear feel that you're trying to move from, let's say, localized perspectives on the world, which deform, let's say, or set up values in this reference system in one way, to a description that considers any possible reference frame, right? And that move from one specific position to any possible one, right?
Yeah.
Will give the general formula.
This relativity of position means that position in itself does not exist, right? There's only position relative to another position. And that's the same theme that you keep going on later. So then rather than the absolute magnitude of something being what determines it, is the ways that it transforms with other things. So it's already a very compositional approach.
Yeah, that's what I wanted to state. Like, there is a very compositional idea, and it's equivalent to talking about our local kind of fixed bargain spaces, and then setting up the problem of how can all possible descriptions of value from any commodity's point of view cohere together, right? That sets up, let's say, value as a sort of equivalence principle, right? Intrinsic value doesn't exist, only this relational version, right?
There we can go. So next is the next big figure is Descartes, who really is the one that started that, well, first formalized Galileo, of course, with Cartesian coordinate systems and everything. But even going further, the really important thing is that sort of directly from the consequences of formalizing Galilean relativity, where you can showing the transformations that allow you to translate between different reference frames, even if they're moving relative to one another, which are just linear transformations, which are just gonna like shear your space. He gets to actually the first time proposing something like the conservation of momentum directly from Galilean relativity. I should mention also this connection on point B here with the symmetries of the laws of physics under translations. That is like I guess the core idea of Galilean relativity. But that led him to conservation of momentum. We already see here talking about how God keeping the world moving at like a constant rate, and that things won't just stop because of like the force of the power of God. And this is his way of saying it. But the first statement of conservation of momentum, which is a big deal for
physics with God in it, was really cool as well, wasn't it? Like,
yeah, the ether and everything.
Yeah. Yeah, we just added this slide here because in the history of relativity, actually Newton plays a weird role, right? Because before Newton, you have a very kind of clear idea of this sort of constantly mobilizing the idea of things being relative to the reference frames, and reference frames being relative to one another And even though the guy kind of explodes into the theme, right, with theory of gravitation, the use of differential calculus, and a sort of ridiculous unification of physics on one hand, and like pretty much the birth of its predictive power, right? On the other hand, there were problems in this sort of Galilean description of relative reference frames, and saying, for example, if I'm in a boat, in a ship, and I draw something inside of it, I mean, even though my pen is moving relative to the water, is moving ahead, relative to the ship and the paper is moving in circles or whatever, and allow you to kind of discern like the locality of the reference from the general. Problems, let's say, concerning inertial forces like rotating around an axis and centrifugal forces and things like this, which couldn't be explained in this sort of relative way, led Newton to keep the idea of an absolute reference frame, right? An absolute space and absolute time, right?
So there's like a universe in the background. This is Newton's idea of the ether, that it's just like always in the background, and there's some universal coordinates.
And
right?
I think
there's like an X, Y, and Z.
Yeah, just an X, Y, and Z.
The center. And
yeah. And I think that the reason why it's good just to mention this is because one of the big kind of interventions that was relevant to Einstein even corresponded with him, is also a reference to Bogdanov, who was the Ernst Mach, right? Ernst Mach was a physicist and a philosopher, and this book of his, Science of Mechanics, was actually a big influence on Einstein, assumedly. And he gives a sort, I like the way Nottale describes his alternative answer to Newton. So Newton would say, look, if you're inside the ship that Galileo imagined, and now you rotate around your own axis like this, like holding a pallet or a bucket or whatever, you will feel your arms stretching. And that system, it seems like it's an intrinsic one with reference to the background. Like it doesn't really matter if you're on a ship, on the water, what's the reference frame, it's gonna have the same sort of forces at stake. And the way that Mach interprets this is by saying that, well, in that case of that rotation, there is a specific reference frame. It's not an absolute one, but it is universal. So it's kind of like saying that just because it's the largest reference frame you can think of that concerns, you know, planets or whatever, it's still a local one. It's kind of local, making local the universal, right? That's why Nottale will say that, in other words, the body would turn with respect to a frame of reference, not absolute, but universal. So you codify the sort of absolute background back into a frame of reference. It's just a very large one, right? So I think it's relevant because you can see that there is sort of return to an idea of relative or local reference frames. And that kind of move, that rhetorical move as well, the sort of whole philosophical approach to this, was influencing Bogdanov and his theory of organization as well. So it's nice to stop there as well, right, on the path to later stuff.
Yeah, the big next step is Emmy Noether, whose Noether's theorem, which, I mean, very generally, you can just say it as to every differentiable symmetry in a space, in this case, if you want to be specific, generated by local actions, there corresponds a conserved current. What that means is anytime you have something that is differentiably conserved, so it's conserved in such a way that you can like turn the dial just a very tiny amount in a continuous way, by local actions, which these are the symmetries, whether it's translation or rotation, or in our case, it's going to be a scale change, that they're going to correspond to some conserved current. So there's going to be the conserved current means there's going to be a conserved quantity, which really here means a physical law, right? But importantly, it's the fact that the symmetries, right, and the ways that things relate to one another in the system give constraints on the forms of the laws of the system. So it's really quite, it's like maybe the most mind-blowing like theorem in physics, and the fact that it works. These like very seemingly unconnected things, but it's generalized quite a lot. I mean, the most basic examples is that translational symmetry gives you conservation of momentum, because if I can move from one place to another place and say that the laws of physics are constant between them, then that implies that your momentum should basically keep going. It's about to change as you translate tiny amounts. I guess so I added this image as well, and I know it's very complicated and looks scary, but the thing that's important to just consider about this is the approach that Emmy Noether uses is basically using perturbation theory, which is, and the idea is that you have this path of like least action, and you push it a little bit in some ways, and you see how it changes. And it's basically, it's based on this very important idea in physics, which I don't know if I have it. I think I have it on the general relativity slide a little bit, but it's the principle of least action, which is basically that like nature, is that nature is lazy, is sort of the best way to think about it, is that with the laws of nature correctly formulated, the true path of something is going to be sort of the path of least resistance. Yeah, so I mean, in the Euclidean world, makes sense that just like a straight line, if something's moving straight, it keeps moving straight, but we get different things when you get relativity. Some more things about Noether's theorem that's interesting. Time symmetry actually implies the conservation of energy, which is very important. And it's also generalizable, and rotational symmetry has to do with conservation of rotational momentum. But it actually generalizes to quantum physics as well. So it's both a theorem that applies on the level of the classical and the quantum. It's called the Ward-Takahashi identity, that also is used to prove things about laws of conservation of electric charge and things like that. But not super important to go into that too detailed.
But it basically sets up the conditions for, let's say, connecting geometrical properties and physical quantities, like energy and geometry, very strictly, right?
Yeah, it gives the way that the constraints on the system form the logic of it, which I think is a very compositional way of thinking. Yeah. So this is probably the one that people would know the most about, just like from cursory knowledge. But special relativity kind of comes from the issue of the discovery of the speed of light as a universal maximum, or universal like constant for all observers. So how we were talking about the classical like relativity of velocity, that you can, it doesn't really matter what speed you're going. When you measure velocity, it's always in reference to something else. But so in, I mean, Einstein's famous train experiment, right? He asks, what is the difference between a light bouncing basically in like a moving train versus just on the ground? Like, should the train like add extra speed to it? But then so special relativity is trying to grapple with that contradiction, right? That you can move reference frames, but the speed of light is always going to be constant no matter what. So
and finding what is a formalism that actually allows you to, again, equate all possible perspectives on these different perspectives of I'm seeing you move, you're seeing my move, but keep the velocity of light constant in any of those, right?
Yeah. So here the important transformation is the Lorentz transformation, which you see here, which I mean is not, you don't have to get bogged down on it, but the most important thing is that you see on this bottom radical, as the velocity goes up, this number will get closer and closer to 0 on the bottom, right? Which will blow up the entire thing. What this really means is that here the speed of light takes the position of an infinite quantity. Because the closer and closer you get to it, the larger and larger this value is going to become when you scale space and time. And this applies to energy and all, basically everything else as well. You also get another invariant called the spacetime interval. And finally here you get really like the big interesting, where relativity starts to get really interesting, is where both space and time become relative concepts. Because in Galilean relativity, time was still absolute, right? A second is always a second. But here, spontaneity is not necessarily always agreed upon. Oh, I didn't finish this line about spontaneity. But basically, spontaneity is not always agreed upon in special relativity. So or simultaneity, sorry. Two events that are simultaneous in one reference frame aren't always simultaneous in another reference frame. This other image. That's right. Oh yeah, sorry, and we can show probably this quickly. Or do you want me to share the screen for that?
This one here,
Or you want to do, yeah.
No, I can share. You can share it if you want, but I can also add it here.
I think I'll make it easier. So this is just will give visualization.
You want to share it from your side?
Yeah, I'll do it. Okay, can you see this?
Yeah, I see it.
Okay, so this gives a visualization of what the Lorentz transformation is doing. So at the origin is going to be like your reference frame, right? The origin reference frame, and it's always going to be considered to be going constant. I mean, relative to itself, right? So you are not moving at a velocity. So there's just this relative velocity. There's a second event that's going to happen somewhere. So I can change. I have three variables. I have relative velocity and the position of event B and the time of event B. So what this diagram is it's called a space-time diagram. So you have just distance on the x-axis and then time on the y-axis. So, I mean, if you want to extend this to like an accurate space-time diagram, it would be really four-dimensional, right? And you would have these, like this picture on that last slide, these light cones. But this is just space with one dimension. These 45-degree angles, because you see this is space, this is time, are going to be the speed of light. So you set the speed of light to be 1. That's what particle physicists always do. And it makes it easy with these space-time diagrams. But the idea is that I can set another event. For example, I can set an event that's one position to the right. So with no relative velocity, they're going at the same velocity. You're going to see their frames of reference are exactly the same. Or really, it's just a shift in transformation. It's just going to be a shift. But then if I increase this 0.1, you'll start to see these blue lines, which are the frame of reference of B with respect to A. So we are A, and then if I shift to B's reference frame, what will the coordinates look like? And you can see as I grow this number, this relative velocity. So as B starts moving faster and faster away, their space gets like squished and squished. 0.6 maybe You see, and it gets squished kind of towards the axis, sort of around the light cones, which this is what, when you talk about special relativity and all this like spatial contraction or stretching is exactly this. So the preserved quantity is not anymore something like absolute time, but it's the space-time interval, which has to do with the geometry of these lines here. But it gives a good intuitive kind of picture. And you can imagine, right? So this one line is like the y-axis. This is the time axis for B, and this is the space axis for B. So it really it stretches their space out quite a lot.
Okay, that's point A to the velocity of light, right?
Yeah. Oh, another thing you can do, you can shift also the time, or both even. You can see here how it changes the way that, so these, I believe, if I remember right, these are the space-time intervals that are preserved. I think it's the distance. I don't remember exactly the definition off the top of my head. Oh, here it is. It's this. Anyways, we can, is that clear? Does that make sense?
So as relative velocity approaches 1, these lines diverge, right?
Yeah. So I mean, when velocity approaches 1, what happens is that event B is going the speed of light, right?
Mm-hmm.
So you see the two lines just completely disappeared. If I go to like here, 0.9, it's squished all of the space that before was here, right? This is, okay, this is, you can see my mouse, yeah? Mm-hmm. This is U at the center. And then this is your light cone. So the light cone is all of the things, or like things are inside your light cone, or everything that is causally related to you, right? Because when the speed of light is a maximum velocity, nothing that is in this region, it can never reach you because they will have to go so quickly as to break the speed of light in order to reach you in this given amount of time. If it's past this, if it's in like this triangle or this triangle. But if it's inside this light cone, this is all of the events. So you think of these as events. It's all of the events that could causally affect A. This light cone is going to be all the events that that A can causally affect. Yeah. But the important thing about these light cones is that the Lorentz transformations always preserve them. They're invariant under them. So anytime I put in any of these numbers, it's always like it's symmetric around these speed of light lines. So that's the way in which it preserves the speed of light while still having relative transformations.
Yeah. Mm-hmm. Just thinking of the example, like imagine there's like a solar flare happening on the sun right now, and the sun is 8 light minutes away from us, right? Mm-hmm. So that would be event B, right?
I mean,
or event B would be
so here event B is after event A. I mean, I can put event B to be here.
Let's say event A
-1.
Event A is we detect the solar flare. Event B is when the solar flare happens, right?
Yeah.
Okay, so this is what. So this would be B is happening in the past.
Yeah. So if B in the past, if its velocity is greater, you can see how the interval. This is going to be the actual time that B experiences as
you were on the flare.
Mm-hmm.
Okay, I see.
Yeah. So as something goes faster, its relative velocity its relative experience of time compared to other things is going to be slower. Its clock ticks slower, and that's what this is getting at. By like sort of the length of how these time intervals here on the time axis are contracted as you do the Lorentz transformation, they get squished. So that's time dilation.
Yeah. In order to maintain light as the absolute
exactly
speed, basically everything else has to give, right? So that
if you clear the diagram and go back to the original one, like the one that B happens on position A.
Yeah, B is happening on position A, but 1 second after here, or one time interval.
B happened, sorry, on position 1 on the x-axis. So in this case, they are on the same time.
Yeah. So this is a good one to think of. So in this reference frame, these are now simultaneous, right? Because they exist on the same line at like y equals 0, right? So then if I increase this by a little bit, you'll see that now this time axis doesn't line up with this one. So if I want to see, this is actually one, let's see if I will actually show it down here. I don't know what the issue is. Oh, there you go. So what this is showing is that in the reference frame of event A and B are simultaneous. That's this black line here, yeah? Now, if we switch to B's perspective, okay, so B is here. So imagine now you're at the center here, but it's these now shifted curvilinear coordinates. B now is slightly behind A. You see, in its own coordinates.
Yeah,
if I shift these
coordinates has changed. It's a different x-axis, or sorry, y-axis.
Exactly. So here, the simultaneity is not maintained, right? These events that were at the same time, from the perspective of A, B doesn't see them happening at the same time.
Yeah, the way that I understand this, like that really helped me to understand what's going on, is to just imagine take this very simply, right? And imagine, okay, I'm here and there is, let's say, this person is moving with reference to me, right? I'm seeing, so this is the distance at temporal, right? So the first thing you want to preserve is that, well, if this is moving relative to me, it's at this time and this distance, right? It should be, so this is A and this is B. You kind of want to imagine that there is some transformation which takes this back, right, to the axis here. And now I need to shift somehow as well relative to that person, right? So that something is preserved. I want this to be preserved, let's say, and this is preserved here. Right, so this is the first thing that you're trying to preserve with the transformations you're doing, right? That if, let's say, if A is distant to B in some amount from its perspective, that if I now have the perspective of B, it should be the same. Like this is the naive first condition. So you can imagine a lot of different kind of transformations that would do this. So C is here as well. So now I need a transformation that also, the kind of geometrical description that if I don't really move B to the origin point, but move C, that this is also at time whatever, that all the other things are kept. But these transformations don't capture that second experimental data you want to keep, which is that no matter how you change what is on the axis, A, B, or C, the velocity of light with reference to all of them should stay constant no matter who is in the frame, right? So the first data, which is the obvious one, or the more common sense one, choose a geometrical description such that transforming from one frame of reference to the other preserves some quantity that is relevant, for example, the distance between people, right? You need to add the second one, which says, and by the way, whatever changes you make to these things, light should be preserved with the same velocity in all frames, right? So if these two are moving, for example, with regards to one another, they might seem to be at the same time or whatever, same distance. And it's the only geometry that does this is this Lorentz transformation thing, right? That allows every point to become the center point while preserving always the same angle with regards to the light cone, right?
Yeah. The important thing to note about this is that it's kind of counterintuitive because it completely changes how you add velocities. You can't just add velocities anymore, right? Because now there's this infinite quantity that you could never pass, but only approach ad infinitum, right? So actually it changes the way that things scale, right?
Yeah, in order to add velocities, you have to first apply the Lorentz transformation, right?
Yes, exactly. You have to scale them by the Lorentz transformation.
You have to scale it, okay. And that's what that
scale them by the Lorentz factor. So this is exactly this.
Right. Yeah, if we were to measure the angle between those blue lines of B versus the black lines of A, that would correspond, that discrepancy corresponds to the...
That's the Lorentz factor, yeah.
Lorentz factor, yeah.
That's what it's called. It's basically how much space is stretched, how much time dilation is happening. It's all kind of in one, right? Because also like there's that classic thing is you seem to like gain more mass as you approach higher speeds. Not really getting more mass, but only getting more mass relative to an outside observer, which is the way in which it sort of becomes, it takes an infinite amount of energy to go the speed of light. I guess it's sort of how it's said. Not that you could ever do that, but
yeah. Now going back to the example of the sun solar flare, I think it's that B is actually space-like initially because the solar flare is happening at time 0, where both A and B is simultaneous, right?
I see what you're saying. Yeah.
But then the light cone of B will intersect with A sometime in the future.
Yeah. So
we can draw like some kind of intersection
point,
right?
Yeah, you can always for every point you can always draw a light cone, and you can see where future light cones intersect, and that's where particles could possibly interact with one another in the future.
Okay.
Right. So there is a literal limit of how far I could go in a certain amount of time that is bounded by the speed of light. So that's like where we talk about the observable universe is the only part of the universe we'll ever see, because if there is any more of it, it would have taken light longer than the age of the universe, right? To reach us.
Yeah, and that's the whole thing where if what is it called, the Hubble effect, the blue shift, when it gets great enough, we won't be able to see the stars anymore, right?
Yeah. Oh yeah, when they get too far, yeah.
When they get too spread out, that light can't catch up to us. Yeah.
So my question actually was by moving B. In this case, the light cone for A is between.
It's the yellow lines, right?
Okay.
So let me show you here. This is a better way of thinking of it, right? Because the vertical is time, and then here now, rather than a one-dimensional space, it's gonna be a two-dimensional space. So I think it's a little bit easier to think of it as a light cone in this way. So the light cone itself, you can think of it like the horizon of what's the word I'm looking for? Of causality, I guess. Horizon of causality is a good way to think of it. Nothing that's outside of it could have an effect on you, right? So things that are outside of it are called space-like, which are things that could, in some reference frame, be considered as simultaneous potentially. And things within the light cone are time-like, which means that they could have an effect, a causal effect on one another. And they could never be simultaneous because you could never have something happening before something that is simultaneous, right? So there's still a structure that's preserved. It's not just that there's no structure to simultaneity, but it's that it has to, it's relative to your reference frame. And there are still constraints on it. Yeah, does that make sense?
It does. I just wanted to in case that I mean, if the light cone for A are defined by those two yellow lines, as we increase speed, say,
I can, oh wait, let me.
The light cones still remain at 45 degrees, don't they?
Yes, that's the point. So that's what special relativity does, is it preserves the universality of the speed of light, which is the most important thing. So these light cones are always preserved under Lorentz transformations. They're never going to change. That gets us to this next, a little bit speculative, not speculative, but just, I guess, a little difference for a second. I just wanted to mention something about this, about points of infinity in physics. Yeah, in general. Well, first, that the speed of light in special relativity really should be thought of as a literally infinite quantity. Like, I'm in the units that we use to measure it, there is a finite quantity to it, but in the sense that it is like unattainable, from special relativity, it has this infinite quality to it. And even here with the preserving of light cones, it's like, it's the invariant of the system. So it's kind of the thing that lies on the edge of everything. And this also gives the suggestion of a connection to having a scale for time and mass, which is not exactly important for what we're doing now, but it's a cool connection.
I think that one thing Yasha and I discussed a lot is that, there is this statement, Nottale, when he's reconstructing this, he makes this point a lot. He hammers this point that the important thing about the speed of light is not that it has a finite amount, but that it has the qualities of an infinite quantity, right? It's workable as a finite quantity, but the crucial thing is that it has properties of an infinite quantity. And we were talking about this a lot, about how it seems like the infinite plays a part in physics of being kind of at this sort of mediator for you to actually geometrize something, to move something from the sort of description of events to actually move to the description of the geometry of the space of the events, right? And there are other examples of this, like the way Penrose also introduces another aspect of infinity to, again, come up with a geometrical kind of a distortion on the shape of some space, right?
Yeah, this is connected to this. I mean, this is a mathematical concept, but I just wanted to mention it, called compactification, which is basically where you have some infinite space and you find a way to sort of take its like infinite horizon or infinite edge and include it within some finite space. So a good example is this famous MC Escher tessellation, which is this actual space that's in is a specific compactification of hyperbolic space, or the upper half hyperbolic plane. So it's called the Poincare disk also, but it's basically this hyperbolic model. And then when you include the point at infinity, this is like imagining taking the edge of the universe and including it, even though it's at like an infinite speed. So it has a similar feel to special relativity, where there's this quantity that plays the role of an infinite quantity, but it still lives in the finite space. And it feels very similar. Penrose has a similar thing, in his Penrose diagrams, where he takes these space-time diagrams we talked about, and he compactifies them in a conformal way, which is important, which means it preserves the angles, that compactifies all of space and all this entire space-time diagram into a finite volume. And he actually uses it to talk about causal structures of black holes and things, which are...
So just to summarize, you get to talk about a finite space with infinite properties, right?
Yes.
So it's
this idea. So for example, if we look in this MC Escher thing, so from outside, it looks like these little guys, little paper guys, fish or whatever they are, get smaller and smaller and smaller. But from the perspective of the space, this is just a negatively curved space, right? So from the perspective of the space, if you lived inside the space, you could just walk to the edge to infinity and you'd never stop. You'd keep going forever. And from the perspective of this compactification, it looked like you're getting smaller and smaller and smaller. But it doesn't necessarily have to be that way. And different perspectives on the space can lead to different ways of looking at it too, right?
Yeah,
because you're getting smaller in comparison to the sphere, then you never get to the edge of the sphere.
Yeah, you get smaller with comparison to the sphere, but it doesn't mean that you can just feel like you're going forward, right?
Yeah.
But I think we should probably go a bit faster because there's a lot of stuff to cover.
Nottale says this as well, just really quick, about the space of having the speed of light as an infinite quantity. But let's just skip directly. Let's go to general relativity. The main things that are important are really, the first thing is the equivalence principle, which is this idea that locally it doesn't make a difference if you are in accelerating or under the force of gravity. What this means basically is that, I mean, the consequence of it is that space being under effect of the force of gravity is exactly the same as a curved space, which if you have a reference frame which is accelerating, it's actually curved because it it goes towards things that it's going towards faster than it's moving away from things. So there's a difference. But this is sort of
I think we can recuperate some of these ideas once we move to Nottale because he constantly talks about them as well.
And I'll just skip over these second two. We'll get back to them about differential forms a little bit in geodesics.
Yeah, I think we can.
As the paths of least action, but we'll get to that. We can probably skip over most of this. Do you want to take on the?
Yeah, I could.
I'm gonna run to the bathroom really quick, but
okay,
go ahead.
Just find where the hell is my.
Wait, am I still sharing? Okay, you can start sharing now again.
Yeah, I mean, I'm just going to go really quickly about this because we actually already discussed it a bit, but it's just that, so Nottale, after he presents this history, what he wants you to think, he takes a cue from a friend of his, another physicist and theoretician, which says, look, you shouldn't really confuse theories constructed on the basis of relativity from the actual principle of relativity. So he takes a couple of chapters to talk about this principle. And the way that he formulates it is very stupid. Like, I think that philosophically, it looks stupid, and it only is ridiculously hard if you think about it from the point of view of physics, right? Because the general formulation is, principle of relativity is that the fundamental laws of nature are valid in any system of reference. I think that having seen like the Galilean relativity, the Einsteinian relativity spectrum in general, you can see how ridiculously complex it is to stitch together, let's say, a formal description or a conceptual description of, for example, rectilinear movement, rest, or acceleration in such a way that the differences between perspectives on these things are equalized in the general description, right? So it's kind of, for the philosopher, it's obvious. There's no relativity involved in saying something like the fundamental laws of nature are valid in any reference system, because metaphysics seems to erase the one thing that makes this difficult, right? Which is the sort of concrete interrelation, causal dependence between, let's say, localized things. But so I found it very interesting that the description of the relativity principle is so unifying, right? So I think discussing Galilean relativity and then like special relativity, as we did in a bit more detail, it's already starts to become clear how difficult it is to come up with a framework, for example, where I can shift the perspective between the guy in the train with the lantern, with the light, and the guy outside of the train as being the perspective on the train, and still make all the crucial relations be covariant, inside that system so that they vary together, right? So it's interesting to see how unbelievably more complicated it gets once you move from the sort of general perspective of, let's say, a worldview of philosophy, of metaphysics, to actually making the local descriptions fit together, right? Or to move from to the general from these local descriptions. So he divides this definition of this principle into two parts. First of all, he's saying, well, the first part is to go along with the idea of that there are fundamental laws of nature, right? On the one hand, he describes it as being the big presupposition of scientific endeavor, that there is some law there. But more important than that is that these laws are unique in the sense that there is some description of these laws that is invariant under all these different frames. It might appear totally different, like apples fall to the floor, but the moon seems to be not falling. So how do you describe the moon's trajectory and apples falling to the ground with the same law, right? There must be some other aspect of that description which accounts for the fact that these two things go about in different ways and so on. But I think that there's another reason why he talks about it, and I don't think we have time to go into this, but it's a bit confusing the way it's written here because of the mathematics, but it also has a connection to that. Part of the debate for Nottale is that there is a competing new theory, a unifying theory of quantum mechanics and relativity theory that actually goes back to Cantor and suggests that you can kind of abdicate from the idea that there is any continuity between levels of description of reality. So you have, let's say, the quantum world, and there is actually a gap or a discrete kind of jump between that level of description and the kind of classical and the relativistic. And you just want a theory that, like, you need kind of to accept there are many theories in the same way that you have like different cardinals and they might be inaccessible to each other and so on. And he says, look, I want to develop something beyond where relativity is today as a sort of framework, but not that far that it compromises the idea that there is some theoretical capacity to unify these different levels of description, right? So just the basic thing. Well, the second part, which is the crucial part really, is that he emphasizes a lot that the correlation of the fundamental laws are with the reference systems, right? So he stresses a lot the crucial development of a coordinate system, that coordinate systems are very tightly related to the fact that scientific statements refer to the results of measurements and not just to observations about the world, right? And he says, well, it's the idea of a system of reference or a reference system that allows us to envision the universality of the principle of relativity. So without this kind of capacity to code observations actually as kind of parts of a system of reference, like as we were doing with A and B in the Minkowski space thing, that's kind of a precondition for you to even imagine how you would solve the sort of different dispositions of quantities in each perspective from a sort of general, for example, geometric description, right? But just going very quickly. So this is, I think it's a good quote, it's worth reading. He says, ultimately, a frame of reference can be defined as an abstract system which synthesizes the universal properties of the mechanism of measurement. That is to say, those which are independent of the specific characteristics of the instruments effectively used, but which are common to all these instruments. So
the important thing I think here is that it's the sort of like gluing together of all of these systems of measurement that are like compatible at a scale, right?
Yeah. So you have a sort of, I mean, the quote kind of constructs this building blocks, right? You have instruments here, in the plural, right? There is something like, not the specific characteristic, but those which are common to these instruments, which will go to the mechanism of measurement, right? And it synthesizes, this would be the frame of reference. So it is in this way that the results of measuring a point's position along one direction is given uniquely by a number expressed using a certain unit associated with an error bar, right? This result requires only the definition of an origin, an axis, and a unit which acts as references, and a resolution for the uncertainty of the measurement, right? So the error is also set in its own unit, right?
Yeah, it makes the error is, the goal is to make the error like an immanent part of the system itself, in a sense.
So the resolution is determined by the minimal unit accessible by a given instrument, for example. The interval between two tick marks closest together on a ruler, for example. However, to obtain results in practice, much more has been required than the quasi-abstract characteristics which are perfect points of origin, an infinitely thin axis and markings traced on this axis. In reality, one must use a wooden, plastic, or other kind of ruler and trace the markings on such and such a method and such a color. All these characteristics which are specific to the ruler actually used disappear as non-significant in the definition of the ruler seen as an archetype of an element of a coordinate system. It is similar with the details of the constitution of a clock. Only the numerical value of the time that it gives is of importance, not the form of its inner composition. But again, he's trying to suggest that that's why he's saying that there is, you don't mind that the clock has some mechanical or electronic way of giving you the ticks and the talks, right? But the common measure, the common thing that you can take from these different instruments is just the measurement of time in seconds, for example. So that's, let's say, this abstracting here, right? And then there is this syntactic abstraction, which is when you move from the correlation between a clock and an event to actually a numerical quantity in a frame of reference, right? Which is this syntactic point he's talking about here. So yeah, anyway, we added this slide because it shows that it frames the whole problem of what a reference frame is, and the passage from one thing to another is actually quite materialistic about, it goes very materialistic about it. It doesn't skip the steps of the fact that rulers have specific, you cannot really, for example, mark the millimeters in a ruler with that much precision, that much more precision than the millimetric, right? So, or it wouldn't even matter up to a certain point, right? And I think it's the beginning of him showing that he's going to take a very kind of, put the sort of measurement in a very active role in the theory that plays a bigger part later on. I think we can actually, this whole thing here, I think we can skip just because we already mentioned it. And it's just him saying that, well, physical quantities are not defined in absolute way. They're relative to the state of the reference system. So quantities are relative to the reference system, but that's philosophical, really, to say that you measure things with regards to references. To actually find a way that you describe this relative aspect takes a lot of effort to find actual physical principles that would account for this. But I think we can go a bit quicker with this. We both like this quote a lot. I think it shows an interesting perspective on how Nottale approaches this. He says, here again, a particular point of view plays an essential role, that which consists of putting oneself in the place of the system under consideration, to envision it from the inside and not only from the outside. It is a matter of placing oneself in the frame of reference best adapt to an understanding of the problem in a sort of empathy with nature. Such mental exertion is required for one to speak of true understanding. One knows because one sees and directly senses, even though virtually, the nature of the system to be understood. Such was the privileged method adopted by Einstein when he anticipated special relativity when he was young, right? In trying to imagine what an observer traveling with a light wave would see. Or later, when he laid the foundations which would lead to general relativity by mentally visualizing the experience of free fall in a gravitational field. So there is something about, again, I think it lends to a nice comparison with what we've been doing in the primer, with this sort of shifting the way of formulating the problem from the extrinsic, what is this to me, right? Or what is this with regards to the space I am in, to the question of what does it mean to see it from that perspective, right? Which is something we've been trying to do, for example, when we say, okay, but what does the commodity see of labor? It's a different way of phrasing the question, and what counts will look very different than when you ask, what is labor in general, for example, right?
This is also the reason why, I mean, in this presentation specifically, we try to avoid those like Julia sets, which show just like the fractal kind of for the fractals, kind of like from the outside for its own sake. So we're trying to imagine a fractal space from within, which in the same way like that, like the MC Escher hyperbolic space, it doesn't look when you're inside of it like it's this weird curved space until you really start moving around or see it from the outside.
Yeah, I think that this really is very, very telling of what Nottale is doing, because the whole problem in the end is the fractal geometry, not fractal objects. He's not interested, for example, in the fact that objects in nature, I mean, he's ultimately going to be able to say things about why so many structures have fractal properties, but it's not really about, look at this leaf, it has a fractal shape or whatever, right? It's precisely, I would say even the opposite, right? It's precisely the way that there where you don't see any of this sort of rich, lush object structure. It's actually the space itself which has the structure, which produces much more weird phenomena than beautiful pictures, right? So it's pretty much about this. I think that we can skip this. I like this because I think it's a nice way to talk about Descartes. He tries to see, I'm just going to skip this, but he basically suggests that what really defines the Cartesian thinking is not the reductive idea that you can analyze the whole by its parts, in the sense that the whole is then the sum of the parts, right? He says that the crucial part of Cartesian thinking is the compositive approach, where you slice things up and glue them back together. But that doesn't mean the method of slicing and the method of gluing is always the same, right? So it's pretty much what you can find in that quote there.
Just a quick question about bibliography. You are not indicating from where you're taking the quotes.
All of the quotes thus far have been from the book that we shared.
They're all from the,
The third
There's
one.
a couple that are from one of the other ones.
Yeah, the other ones, I'll let you guys know where they appear. They actually have a different font. But all the quotes thus far are from
to revisit this afterwards, just to know. Okay.
Sure. I have a kind of a indexing of most of the quotes. I can send you the file, like where you can find them as well. So anyway, this is just the sort of, I think that ultimately he says, okay, relativity principle has something to do with being able to adopt the embedded perspective of the frame of reference, right? But at the same time, posing questions of how do you generalize what remains invariant once you see the difference between these different perspectives, right? And at the same time, it has a sort of compositional feel to it, because he will kind of suggest that there is a very intricate relationship between the Cartesian approach and the relativistic one, where these different parsings out, right, of how things look from perspectives, they're not going to be stitched up back into this general description, like in a mechanical way, where it's just the sum of the parts. It might look very weird the way that you glue them back together, right? And I think the Lorentz transformation that we were seeing are a good example of what a synthesis of kind of local frames of reference looks like. It looks like none of them, right? So I don't know. I just think it's a good point to hold, having in mind.
Here's more about sort of where diagnosing physics today, right? And like why this is even something that's necessary, right?
Yeah, I think we can go. I mean, he doesn't go much further than the sort of common sense idea that, I mean, he goes into some detail, but the fact that the mathematical tools and the rules which govern like high energy particle physics and classical mechanics and this and that, they actually diverge a lot. There's no really, not only not only a distinction of the phenomena's logic, but the tools to discuss and capture that logic is also very distinct. He calls it like a quasi-schizophrenic.
It was pretty good.
And give some comparison of the two. Quantum theory is an algebraic theory with a kind of axiomatic basis. Relativity is geometric.
So there's a clear bias for more spatial based theories, right? So his critique of quantum theory is that essentially it's just getting these axiomatics from a bunch of like direct observations, right?
Yeah. And I think that there is this,
rather than having it based on a geometrical notion at its core.
Yeah, I think that's a principle of what he calls this relativity approach or method that we didn't really highlight there, but it's a constant that he's also cherishing all the time in all the examples, that they always have some, the way that you get to generalize from these multiple references is usually by finding new properties or a new geometrical description, right? You don't move to just axiomatically deducing what the quantities will be under certain conditions. You actually get this global geometric theory, right? Anyway, but just so we can move a bit quicker to the point that he actually proposes to intervene, right? So he says this dichotomy is very troubling. So, I mean, the way when you get to this point of the book, you see that he is telling you that the principle of relativity is a stronger principle than the relativistic theories. It's more general. It's a way of approaching science, and he's saying that well, quantum mechanics is unbelievably successful, but its foundations are not really in line with those principles, right? And I think that well, then he goes back to Einstein and say. That he sides with, I mean, that Einstein's approach to quantum mechanics was actually more sophisticated than the classic God doesn't throw dice, but at the same time, that there was something about it that he was unhappy with. And I think that this is one of the crucial points. He doesn't want to substitute the methods of quantum mechanics, like probabilistic approach to complex wave functions or whatever, for something else. But he wants to show that it's not a matter of, for example, with, I think, quantum field theory, right? Coming up with a geometric description out of the probabilistic tools, but inverting and saying, what is the geometry underlying the quantum world, such that probabilistic approach is the best one for it, or is so effective for it, right? So it's not letting go of everything that was accomplished, but it's kind of trying to add to it a sort of foundational approach that is coherent with the relativistic one, right? Yeah. I think
so this is where he starts getting into the assumption of differentiability in physics. That there's always so he takes the assumption of continuity of space as sort of like a tautology, that space has to be connected in some way, in a way that is continuous and it doesn't just break up. But he says that the hypothesis of differentiability, basically assuming that space is like at its simplest, just gets simpler and simpler and like flatter and flatter, is potentially a thing that we can throw out, and what the, I guess, consequences of it is. I don't know if there's...
Yeah, I really like the way that he describes it, right? So he says that the symptomatic point is that for all the Riemannian geometry and crazy stuff that we have with relativity, you still have this sort of underlying assumption that locally, if you refine your analysis to the most precise one, you're always converging and you're getting the most precise measurement, right? And he says, well, but this is an assumption that is, I'm not going to add a new principle. I'm going to remove a principle, right? So he's actually trying to suggest that you can generalize relativity by removing a constraint. that is only valid under certain conditions and not universally valid, right? And I love the fact that he doesn't do this because of some crazy impetus. His motivation is that it's not, I like it that it's not
even very actual.
It's very actual, and it's not only, let's say, the experimental results, but the practice of experimentation, right? It's as we will see a bit later on when he discusses, like, he makes a critique of the use of differential equations and the physical interpretation of them. The whole point is that nobody actually works like this in practice, right? And so it's a very practical point, in fact. And he mobilizes Descartes here to say differentiability is like, has a Cartesian, you can make a Cartesian critique of differentiability by saying that this sort of refinement to a point, and then the sum of all points gives you back the whole, which is, let's say, integrating all this region back gives you the whole shape of the thing. That's not what Descartes is about. Descartes is about just finding the right parsing of the space. That would be the Cartesian space, not finding the parts that will guarantee that their sum is back equal to the whole, right? So for him, you are actually applying Descartes or the Cartesian method to something like the substructure of these spaces, right? Yeah, so here we just have an explanation of this.
Sorry, can you go back to the previous slide? A solution can be found to this problem by applying Cartesian analysis at a deeper level. Spacetime itself possesses an internal substructure in the space of scales to which differential calculus can be applied, even in the case where it is not differentiable. I don't understand this sentence.
Yeah, this is what the next slide is about.
Yeah. We'll get into this. So, I mean, this is about what Gabriel's talking about, how when you zoom in and zoom in, even in all the contemporary models of classical physics, they're always modeling it as a differentiable manifold, meaning that you can zoom in and it's gonna eventually look locally flat, like this image here of, I suppose, the experience of, on the right, the flat earthers, where they see that the world around them is flat, therefore everything, but really we're seeing what's going to happen without this assumption.
Yeah, with differential calculus, I think it's easier because the idea, right, is that if you take the difference here and you reduce it as much as you can, it will become just a tangent, like the straight tangent of the point, right? It's for a line what this means for a surface, right?
Yeah, so that's sort of the way that, I guess, differential equation, we'll get into this a little later, still gets saved. So it's not like all of differential equations applying to physics suddenly has to be thrown out. It just has to be looked at in a different light. And ultimately, it's how you look at these tangent spaces, which is really what, I mean, when you get into, like, this is what Gabriel and I were talking about a little bit earlier, like the categorification of differential calculus in general has to do much more with these tangent spaces and how they interact with one another.
So, I mean, you just take the differentiability hypothesis this far to mean that if you if you refine the limit, let's say, of your resolution to smaller and smaller intervals, you should be converging on a point, right? So that, let's say, the immediately point in its vicinity, it's like they're Euclidean, their relation, right? The local relations between neighboring points is Euclidean.
And this is also, this is also the way in which people often say that quantum mechanics is like the most fundamental of the physics theories, simply because it's the smallest, right?
Yeah.
So therefore it must be able to affect everything at a larger scale. So that has to do with this hypothesis.
Actually, I understand this, but I didn't understand the correlation, because the sentence above this said that unlike Cartesian mentality or framework, that when you get smaller, the things get less complex.
Yeah, but that's what he says. This is, for him, this is not what Descartes means.
Okay.
For him, Descartes means that when you get to the smaller, the connection, let me see if I can find the actual quote here about Descartes.
Yeah, but in the tangential, like in the differential space, when you make it, it actually makes it smaller. So when you go to the derivative of a particular at a particular point, you get a slope of a line, as opposed to the curvature of the curve itself. Makes it a lot simpler to deal with. That's the whole point. Whereas what he's saying is, as a matter of fact, in quantum mechanics, when you go to the electron, then things get more complex. So these seems to be two different approaches.
Yeah, like, but that's his point. Approaches. Yeah, that's why he tries to separate Cartesian thinking from the idea that the part is simple and the whole is complex. For him, Cartesian thinking is about the fact that you understand not by going to the part because it's simpler, but by going to the part because you understand the composition between parts and wholes.
I see. Okay.
So for him, when he says something like applying Cartesian analysis at a deeper level means that there are parts inside the point, right? So why stop at the point of at the locally flat Euclidean?
So then how do you reconcile? I got this. How do you reconcile with this analysis of differentiability based on a curvature and the tangent line? Because tangent line is a lot simpler than the curvature.
Yeah.
So yeah, we'll get into this. Maybe I think is it actually on the next slide? Yeah, it is actually where I described this. So this is sort of what giving up the hypothesis of differentiability implies. And I think this is the core of Nottale's argument and like contribution. It's kind of like his equivalence principle, but for his thing. So he has a claim, and he actually calls it a theorem, that if you give up this assumption of the differentiability of space-time, it implies scale relativity. So this is very intuitive.
Okay.
It's like
so giving up of this. That's why now. Now he wants to give it up.
Yes.
Okay.
Yeah.
Okay.
Yeah.
Now that makes sense. I was losing my mind. Okay.
Yeah, but this is why he says here, dude, relinquish.
Relinquish. Okay. Now you get why I was confused. I thought that he's keeping it and he's trying to.
No.
Yeah, no.
This is just explaining what it is.
Okay.
Yeah.
All right.
So here, this is what happens when you get rid of it. So it's very intuitive. This is like the classic, and we'll show an image and things of this later, of like the measuring the coastline example, where getting finer and finer measurements does not necessarily give you better and better results, or the results can become much more complicated if you get finer measurements, if you have this kind of rough fractal surface.
Yeah, finer doesn't mean simpler, right?
Exactly. So really the way that he is still able to keep the physics from before, like the differential calculus and everything, is by, when you drop it, you now, instead of having a single tangent space at a point, so instead of you having this smooth space that has one point and has a tangent space, or I mean, if it's a curve, it's a tangent line. Now you have a whole set of tangents that's a continuum of them that depend on the resolution. So for each resolution, you have a certain tangent. So I included these Menger sponges, which is just another fractal example, on the bottom, just to get a good visualization. You can see there's a resolution range, right? Which is from very, very far up until you get to the size of this biggest hole, in which this surface seems flat. It seems just like a cube. Then when you get to a smaller resolution, you can eventually tell the difference between this first, it's like this first iteration. At a certain resolution, you can see this first iteration. At the next resolution, you can see this. So it actually becomes more and more complicated and more bumpy as you go, and not necessarily converging to something that's simpler than what it looks like from the outside.
Yeah, I think we'll give a good example of this in a couple of slides.
And the important thing really that you get from this, from scalar relativity, is that structure arises at all scales. It's not necessarily reducible to lower or higher ones.
But now I think that this is a good point to introduce something which I think is, at least for me, was the opposite principle of how I usually approach this. Like, I think most of our discussions have been about stating that there are many scales, or scales make a difference. But his point is scale relativity, meaning he's not giving you, there are different reference frames depending on your scale only. He's trying to find out what is a general description such that when you vary those scalar principles, the description remains the same, or it's conditioned by those changes and it obtains for both, right? So I think it's also important to see this, that it's not a matter simply of announcing there are different scales. It's a matter of unifying the theories such that scales are variables in the theory. I think that's a slightly different thing. Mm-hmm. Becomes clearer as we go, I think.
Yeah.
I like this. I posted all of this because I think this is actually quite important. It's a section from the other book. So the Scale Relativity and Fractal Spacetime is the first page of chapter 3. I'll just go over it because I think you can see the motivation for scale relativity in a quite concrete way, right? So it starts talking about take this differentiable function, right? The way that it's defined, its derivative is defined by Newton and Leibniz. So you just have like, take the derivative to the limit here, and this is the equation for it. So you could easily compute its limit and find what is the actual derivative for it. And well, there was the whole discussion back in the day, right? Like Berkeley and all the guys, like even Hegel in a way, were caught up with the idea of what does it mean to take something to an infinite limit? What would infinitesimals mean and so on? And
yeah. In that structure, it wasn't a rigorous definition.
Yeah, it wasn't a rigorous definition, but I like the way that he divides the discussion. He says, mathematically, the modern definition of limits is an answer to Berkeley's criticism. Mm-hmm. Like, 100%. We saw that issue is not a problem anymore, mathematically speaking. But then there is a different question. Does the mathematical definition of derivative agree with its physical meaning? So even in the coherent, formally rigorous mathematical version of limits, what is the physical interpretation of this, right? So it's a slightly different question. It's a question about the thinking of physics, not the mathematical theory behind the thinking of physics, right? And he says, well, it's clear that this is not the case in reality, right? So it's easy to show that this is not the case and that the mathematical derivative is an ideal concept, which is very far from what's actually done in physics. So if you take, for example, the motion of a point-length body, this is how you define its velocity. In order to evaluate the validity of such a definition, let us attempt to perform a thought experiment. If really the physical velocity was to be defined in this way, this would involve our ability to make measurements of the position of the body on time intervals, say of 1 second, and then changing the order of magnitudes to very, very small quantities, right, of time. And we will recover the problem of the Kantian antinomies, according to which the 0 point is actually unreachable, blah, blah, blah. And
here, the Kantian antinomy comes back sort of because of quantum mechanics, right?
Yeah, but
because when you get to these smaller and smaller scales, it takes higher and higher energy. I think he says that later.
Yeah, but I think that at that point, he's talking still about just the kind of conceptual problem of what does it mean to measure infinitely smaller quantities. But I think that this is the important point here. He says, why would an infinite series of measurements have no physical meaning, right? First, because we're unable to make measurements of position and time below some minimal resolution scale. However, this minimum resolution scale depends on the quality of our measurement apparatus and is indeed one of the main progress of experimental physics since the discovery of the microscope to continuously improve the resolution. So this is kind of a relative critique of the thought experiment, but not complete. Then he says, well, the second one is that the number is infinite. So even though one may hope that you could measure at a very, 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 very small resolution, measuring at the limit is definitely impossible. And he says, well, the first thing that I think is a consistent critique he makes is that actually in practice, you don't solve these equations by taking them to the actual limit. You solve them by actually this polynomial redescription with the Taylor series and coming up with, let's say, very, very good approximations to them, right? But this is, I think, the crucial part. He says, experimental physics has brought a fundamental denial to the view that there is a physical interpretation to mathematical limits. If one really performs the experiment of measuring positions in instants with smaller and smaller space and time resolution intervals, one rather rapidly reaches scales where the quantum laws manifest themselves. Instead of the expected vanishing difference, the velocity becomes more and more badly defined with decreasing scale according to Heisenberg's relation. So the fundamental contradiction has led Heisenberg to construct the quantum theory on the basis of giving up classical concepts of position and velocity. However, from the above analysis, the key hypotheses which seem to be falsified is the assumption of differentiability of position variables, right? There is of space and not their very existence. So he says, it's not that quantum theory doesn't need to have concepts of position and velocity. It's that their interpretation as part of a differentiable space, like an Euclidean space, which is where we're accustomed to define them, those are the ones that are being questioned, right? And that the equivalent, another way of showing the same contradiction is that the same relations tell us that if one wants to perform an experiment, like measuring a position or decreasing time resolution, one needs an increasing amount of energy. So the construction of experimental devices aiming at scanning the microscopic world has definitely confirmed this fundamental fact, blah, 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 that you would need infinite energy to actually measure something at an infinitesimal, at the limit point, right? So
in fact, anything below the Planck length,
Planck sphere, yeah. So, I mean, his justification is that in practice, we already don't treat space as differentiable. We either use Taylor series to approximate, or we have limits coming from the experimental apparatus, which imply that you can't really have, let's say, full differentiability of space, right? Even at the current state of physics, that's not what you already do, right? I think we can actually just skip this part here because we can return to it. I just wanted to glue directly to this point, which I think kind of ties it together since we have kind of a limited amount of time. So he goes back to this and says, I think this quote is really good. He says, if the mathematical point can have a proper definition, is it the same for a physical point? Can one bring into existence a true point? The question can also be asked about other geometrical objects such as line surfaces supposedly without thickness. If one wishes to explain what a point is to a child, one can simply draw a dot. But what has one actually done? The sheet, board, computer screen upon which the point is drawn, even the receptors that are used to detect this image, are in actuality characterized by a certain limiting resolution. The dot on the page or screen may be smaller than this resolution, but it still has nothing to do with the mathematical point, which must be strictly zero in extension. One can simply examine it with a magnifying glass to realize that it's in fact an extended spot, right? The mathematical point on line ultimately cannot be physically realized. And I think that he makes a really important point on distinguishing theories in physics from mathematical tools for describing those theories, right? And it's kind of like a correction course. Even though mathematics is ridiculously powerful, mathematized physics, you shouldn't really confuse your concepts in physics with their mathematical description, right? And I think that this last point here for me is the best formulation of the motivation of his approach. That's why I just fast forward a bit. So what should we replace the mathematical point, curve, or surface with if they are in actuality inadequate for physical description? The answer is a mathematical tool which includes in its definition itself what the physicist does in practice. One magnifies them more and more with a lens, then with an optical microscope, then with an electron microscope, then a field emission microscope, then a particle accelerator. All these instruments change the scale of observation. Towards the larger scales, the use of glasses and telescopes play a similar role. Yet what the experiment and observation taught us is that never in the course of this type of operation does the strict equivalence of these mathematical objects appear. These objects which are nonetheless used to describe the world. So by improving the resolution of an instrument, new internal structures will always appear. But a new geometry now exists precisely characterized by the existence of structures at every scale, which is fractal geometry. So you see, like, the motivation for fractal geometry. Sorry?
That's the whole point then. That's what...
Yes. Yeah, exactly. So it's to take something which does not appear in the mathematical grammar of physics, but appears in the actual experience of the physicist and of physical development in physics, right? Which is this correlation between measurement resolution and the construction of mathematical objects, right?
And the elegant thing is that it does this materialist interpretation, but in a relativist, like a classical relativist way.
Yeah.
So it starts on very simple premises.
Yeah, so, I mean, I kind of skipped this, but we can go back to it. I mean, this is just like a scale, right, of different kind of physical phenomena that you can, like the human scale, the radius of the Earth, and so on and so forth, and the different magnitudes that you have here, right? And we thought about adding on the side of this, the actual discontinuous type of instruments of measure that actually capture what we call the resolution range for these different scales, right?
Yeah, and there can also be like many different resolution ranges. Like we have, I mean, on the very small, there's the quantum, there's the classical, and then, but even within the classical range, right? There is the range that is kind of like described by Newton. Then there's like bigger described by Einstein. So there's sort of ranges within ranges as well. But
yeah, you could. I think a good way to do this would be to imagine, for example, if we could add, for example, particle accelerators, like would be something like between here and I don't know here. Then you have some other types of electronic microscopes or whatever for this region here. Then you have something like regular rulers or eyes at some scale. Then you have telescopes or whatever. But then you can actually add the fact that physical theories, they do something like this, right? For example, Newton would do something like this. Einstein would do something like this, or actually a bit smaller, right? But like something like this, right? So you can have resolutions being integrated into bigger theories that describe more than one data that you can capture with more than one instrument of measure, right? To construct a theory of reference that is actually accepting inputs from many instruments and unifying them in one single kind of lawful description.
So yeah, I like how
sorry, go ahead.
I was just gonna say this materialist interpretation, it allows a really nice interpretation of how scientific theories build upon themselves. And not simply that previous scientific theories were wrong, but they were applied in a specific like scale space. And that I think is a very elegant way at looking at the transition of scientific theories. Anyways, go ahead, Reza.
Yeah, I just wanted to tie this back to the relinquishing of the differentiability principle. So we are, by changing these scales, we find structures that are not necessarily continuous as we go.
No. So they are continuous. They are continuous, but not necessarily differentiable. The idea is that when you give up the differentiability, you can have space itself look very rough as you zoom in. So the emergent laws of nature between these different scales are going to be different.
So for example, I think we can take like the example would be the one we skipped here, right? Which is this one, right? The classic example of measuring the coast of Britain, right? Depending on the resolution you measure, the size actually changes. They don't converge, right?
Yeah. So what this
have you seen this?
Like these boxes, they give you what's a way to calculate what's called the fractal dimension. So basically, it's how these boxes scale. So if you imagine the coast of Britain being perfectly smooth all around, as these boxes got smaller and smaller, the area would simply go to 0. Yeah. But because it's so kind of rough and fractally, at least, you know, at this scale, as these boxes get smaller, it actually preserves somewhat more of an area. So the scale of the size of your ruler will change quite a lot about the measurement, and not only change something about the measurement, but also give a different context in which that measurement is relevant, right? So at this very large scale, maybe those kinds of measurements are useful for like the motion of ships in the ocean and things, but for like a seagull would maybe need the smaller resolution, right?
The JP has something that seems to be important here.
Yeah, just pointing out that Wolfram's model actually, or there's other people, but Wolfram has a model where he drops continuity but keeps differential. Yeah. So that would be like, as you zoom in, you see actually that the scale, the coastline is actually a bunch of disconnected points, discrete points, and it's only from far away that it looks like a continuous coastline. So there's dropping, you can drop continuity, keep differentiability, but here we are dropping differentiability but keeping continuity.
Yeah. And I think that just before we go to the path integral thing, I think that this is helpful, right? I mean, this first, I love that he actually uses the same as your delta thing, then is because, so I think that the basic kind of idea to understand this is, imagine that rather than just having like 3 axes, 3 coordinates of time, of space and 1 of time, you also add, as it does here, like resolutions for every one of them. So at which resolution you're measuring each one of them, right? What is the unit that goes with them? So let's say this is, you have the distance between A and B, right? So for example, if you're measuring it with, I don't know, millimeters or perhaps meters, right? So you have like a ruler that is like this, and this is, I don't know, centimeter, or you have much smaller. The measurement of this in centimeters and the measurement of this in millimeters, and then you sum it up together, will converge, right? It's like you're making more precise. But if you continue making the resolution larger, it will more and more look like A and B are actually just superposed at the same point, right? On this side. And if you make it smaller and smaller and smaller, so your ruler actually becomes smaller and smaller in this way, or like you zoomed in here, it doesn't converge, because imagine that we have a very, very, very small ant moving here. Like there are small irregularities and roughnesses to this distance here, right? You actually would start getting a larger distance, right? And not simply coherent or converging to a point. So the idea is that if you go to very small, you would actually get, let's say, a weird fractal path that goes like this, right? And if you zoom into part of it, it's actually, this part of it is actually even more complicated, and you can zoom into it even more, and you get more structure. So the smaller the resolution, this distance between A and B actually can become an infinite path, right? So it's actually a continuous of resolutions here, right? And some thresholds where it was differentiable, and then it's no longer differentiable here or here, but it might become again differentiable here. Like it depends on the actual structure, right? It can be self-similar, for example, in some sense. But I think this gives a good idea of like what it means to make this explicit, right? It's like adding more coordinates to your definition of something on a reference frame, where these added coordinates are giving you the unit you're using. And well, if you describe the distance between points in some specific resolutions, for example, you might start to find that space is affected by some non-differentiable property, some crazy thing, right? I think that the path integral helps at this point, right?
Yeah, it's important that the space becomes not like, the reference frames are not only like this little like set of coordinates at each point, but it's also the size of the ticks on your ruler, right? But to get to the Feynman's path integral, he actually has this really great quote where Feynman seems to kind of almost suggest something along these lines already, where he says, typical paths of a quantum mechanical particle are highly irregular on a fine scale. Thus, although a mean velocity can be defined, no mean square velocity exists at any point. In other words, the paths are non-differentiable. Basically, what he's saying is that you can't define for these paths integral, which I'll describe in a second. You can't define an instantaneous point velocity, even though you can find average velocities over lengths. Here, this is actually from this quote I actually found in this book, because Nottale quotes this in one of his books. But this is from Feynman's book itself on the path integrals. But the idea is that he was basically trying to solve the principle of least action for quantum mechanics, but then quantum field theory. But the idea, really, the crazy thing he did was, in order to actually solve for the action, he integrated over infinitely many paths. So all possible paths. So basically to find like the energy required for, or like the true path that the particle is going to take, he takes a sum over the action, which is basically like how much resistance there is to that path, but over all possible paths, which is this huge infinite space of paths. But he does some fancy renormalization things that allows it to be manageable. But the point is that when he sums up, and this path integral formulation works like tremendously well, and it's kind of the one of the basis of quantum field theory. But it can be sort of thought of as like similar to, you know, Einstein's, for Einstein, what this absoluteness of the speed of light is for Nottale's theory. It's the one thing that suggests that there is a reason why this might actually be interesting within physics itself.
Yeah. And I think that part of what the actual nitty-gritty of what Nottale does, that this approach here that I mentioned with what he calls super systems, that includes the explicitation of the resolutions that they're being measured, they're just the first approach that he takes. Afterwards, he tries to come up with this sort of non-differential geometry that actually encodes directly allows you to derive a more general version of the Lorentz transformations and things like this, right? And
I tried to make a kind of a visualization of how we should be thinking of these scale spaces, and specifically the frames of reference. So I mean, as a reference, right? So here, this is sort of a picture where maybe at the top is something like Einstein's theory, right? You have this smooth manifold of space that shows how the planets orbit around each other. But you also have a way, so at each point you have a little reference system that is not just your coordinates. So like, which way are you pointing? How do you actually do geometry? How do you add angles and things? But it also includes how you move smoothly between these reference systems. But the important thing is that as you go smaller and smaller, the resolutions on these change, right? So you can both move laterally, you can move like within a scale space, or you can move between scales where you actually get smaller and smaller resolutions. And you see these paths. So I tried to draw them in purple if you can see them. Here, this is a very smooth path. This one becomes kind of more fractally. And here, this one is kind of going all over the place. And this is almost looks like it has like a two-dimensional fractal thickness to it, right?
Something happened here.
Yeah, no problem. But so you can imagine each one of these low coordinate frames is basically a tangent space at each local point. And really the way that, right, we mentioned how you get back differential equations is by how these tangent spaces are connected at different scales. So the thing is that really what's interesting is that emergent phenomena are supposed to arise in the ways that these tangent spaces are mutually incompatible, right? So if space was completely smooth and flat, but all of them, there would be one single tangent space. There would be a point, and you'd have a tangent at that point, and there would be the single tangent space that would agree for all scales.
Yeah.
But here it's different. Here it's saying, if I'm taking a smaller resolution, these tangent spaces suddenly can look very complicated and kind of go on top of each other, even though they look like they're smooth from a larger scale. And I mean, this way in which they're connected feels, which is just one thing I want to mention, it feels very much like a sheaf condition, right?
Yeah, it does.
The way in which they're glued between resolution ranges.
What I wanted just to take advantage of, like Caron added a quote here from Wilson. I mean, we'll get a chance to talk about this, I think, next time. But I like the way that, I mean, Wilson proposes that, you know, you kind of respect the difference of what he calls the adapted, right? The localized model.
It's the RVE. He calls RVE the representative volume element. It's like the delta thingy there in the
so the delta thingy corresponds to some way of describing things, right? And then you kind of parcel them in this different conceptual language together, kind of admitting that there need to be a bit flexible and so on. But I think that here the point is that what Nottale is trying to do is from the other side. It's not trying to give you a sort of pragmatic, a theory of the physicist's pragmatism. Like Feynman, when he's talking about relativity, will use some language, will allow some things to be left in the background. Some things don't make a difference, and you need to respect this to talk about things with precision. And then you move to a different RVE, and then something else kind of organizes the language that is properly descriptive at that space. And you need a sort of pragmatics of moving between these models, right? Nottale is taking the opposite path and trying to describe the geometry that gives rise to the need for different models at different scales, right? He's actually trying to give you, that's why scalar relativity is weirdly about the continuity and not the discontinuity between scales, right? It wants to output the discontinuity by inputting the proper geometric description, right? If you take the right generalization, it should allow you to have resolutions as an explicit variable that output why it is that some language works on some level and some other way of talking about does the work for another level, right? It's kind of companion piece in that way.
I see. I
think it goes very nicely together. Yeah, so we added
one point on the previous. Also, I was thinking about whether this is a sheaf or not. I think so. We have the conditions of the pre-sheaf, which is that as you basically zoom in, you have restriction maps on the tangent, this blue stuff, right? It's just the tangent information, space information. And then, so that is already a pre-sheaf, I think. But then in order to make it a sheaf, we have to say, if you were to draw two of these black circles and they had some intersection, some agreement, we should be able to like glue them together back to have the same, to have a unique tangent bundle or tangent information, right? Assigned to those two black circles.
Yeah, I think it's something like that.
Yeah, so I think what we could, if I'm understanding correctly, we could say that the non-differentiability is establishing a sort of space of these different kind of pre-sheaf conditions because they organize different restrictions of the space. But what we call actually the physical theories of each, let's say, consistent level of description, it gives you the sheafing condition of gluing these things consistently according to some quantum field theory or classical mechanics or whatever.
Yeah, right? That's kind of what I was thinking.
Right, if these things appear under these restrictions in this level, and I can actually causally relate them probabilistically or classically to some recursive function, whatever, and then in that other way, then that gives you the syntactic perspective back.
Yeah, that was what I was thinking.
With the earlier thing you were mentioning about how this is the additional thing to add to the Cartesian way of thinking, right?
Yeah.
That the relationship between whole and parts is not so straightforward, where knowing about decomposing whole into parts does not mean you know how the parts glue back to the whole.
Yeah, I really like, because this really touches on what we were trying to do last time, this sort of the collective worker as the set of parts of the labor power that doesn't glue back to the worker, to the bundle of workers, right? That idea was pretty much like, you have this sort of individual sets, but there are ways of, like, there are resolutions at which you decompose them, right? Which, for example, make this a relevant part, and this a relevant part, and this, and this. So that if you take if you synthesize them back together to see them as a kind of the set of these parts, this set is different from just taking, you know, the set of these two things, right?
Yeah.
So I think that you recover the proper scalar dialectic, so to speak, is one where you have a whole and it assigns some analytic description of its parts, but there can be an alternative analytic description of its parts that, so this goes here, and that goes to some other whole, right? So I think that ultimately what we're trying to understand, and I think what Nottale really helps out with, is that it shows that composition can really be a principle for, like, it is a constant combination of finding the right analytics and the right analytic conditions. Like, I mean, if you go back to the idea of real atoms in Badiou, right, those three conditions, the analytic condition, find the minimal part. In physics, you even have the minimal part having an equivalence principle, right? So find the minimal part such that something becomes indistinguishable inside of it. Find a way to generate connections between it so that you can actually synthesize it back onto a glued space, but do it in such a way that this is materially conditioned, right? It's the postulate of materialism. It's not just a symbolic atom, it's a real atom. So you need to be able to project that sort of predicative structure of parts and wholes onto the parts and of the space itself. You're not synthesizing back predicates. You're synthesizing the parts of the world you distinguish through the predicates, right? Mm-hmm. So in physics, the parts of the world actually are guaranteed by the experimental counterpart, not by the theoretical description, right?
That's where the whole cost of instrument.
Yeah.
Like,
so you could come up with a, let's say, Lucretian description of atoms. They are the most minimal, indivisible, below the Planck scale. That is an atom in a sort of conceptual language, and it can come up with a view of everything. But it will be a metaphysical view and not a theory of physics, because it cannot have the material counterpart. It won't be projectable onto parts of the world that can then be in themselves glued back together, and they're gluing tested by predictions, experiments, and so on, right? Which will go take a portion of the world and check if the parts are coherent as we predicted them to be, right?
I think we should mention something also, because I don't think we mentioned this before, but in Nottale's theory, the Planck scale takes the same position as the speed of light takes in special relativity, as this like finite quantity that has the properties of an infinite one, right?
Yeah.
It takes an infinite amount of energy to measure things at the Planck scale, right?
Yeah. It's amazing, right? Because it's a zooming invariance, right? Mm-hmm. If you try to zoom beyond that scale, it's like you're actually dealing with an infinite zoom. You never really, you can't reach zooming beyond it, right? So I think just to conclude, like, we separated some ideas. I think we spoke about this one a bit, right? That the idea of structure emerging at all scales, that fractal geometry keeping continuity and undoing differentiability, it allows you to let go of the idea that the smaller is the simpler, right? As a general, which I think is a very profound idea to let go. It's not very simple to adopt that perspective, in fact.
These are some good pictures from one of his books.
Yeah, I really like
on what this would look like. Yeah.
And I think that this is also helpful because this is the sort of fractal that interests me. It's not really interested in the self-similar or the Julia stuff. It's just the idea that if you change the resolution, these are just changes in resolution. And right, I mean, taking this path here and taking this path here and then this path, right? And then this ridiculously tortuous rough path and then this infinite one where you can't really differentiate it at all, right? They're just by changing the resolution, you get such different landscapes. I think that, well, another thing that we thought was really good is just that he clearly makes a connection between the types of structure that are accessible in a given system of reference and the types of measurement that are experimentally possible in that context, right? So to go back to our definitions of resolution and scale at the beginning, you have the analytic and the syntactic conditions we talked about, the analytic predication, the syntactic kind of operation that changes how you describe the world from that point of view, but also this material condition that it needs to be, I think that it would be interesting to further study in which sense experimentation is what allows you to actually assess if your synthesis concerns the predicates or the parts of the world, right? The whole projective representation thing in the transcendental functor. I think it would be a good place to make that distinction. It's almost like a nice distinction between metaphysics and physics, right? Metaphysics gives you good analytic and syntactic principles. Everything is made of water, and then you build a beautiful theory where everything fits. But you can't really project that back on stuff in the world, and then through the relation between things in the world, assess the validity of it, right? It's metaphysical in the sense of not really negotiating with material conditions, right? At this point here, I think it's very, very profound. I think I ranted about this with Dennis someday over WhatsApp, but one of the really cool,
I was just saying, this is connected to the way in which fractals actually come about in nature, right?
Yeah. So, I mean, he tries to show something here, which is, he's trying to talk about why are there fractals in nature? And he gives two answers that are very important. One is that, well, if we are correct, the question is not why there are fractal structures, but why are there smooth structures? Because fractal geometry is more general than differential geometry. It's not a restricted version for talking about weird phenomena. It's just differential geometry without the hypothesis of differentiation. So it's the broadest one, right? And the second thing that he talks more with regards to natural phenomena is that fractal structures can be obtained in terms of process of optimization under constraint. So for example, one of the examples that he gives that I think it's really good is this one. So he says, imagine that you have some animal, right? Like some basic creature that has, let's say, like this. So it has some surface area, right? And some volume. So the membrane here is mediating how much energy it can take from the environment, right? But the volume is determining how much energy it actually needs to kind of be, what needs to be fed. If you were to scale this times 2, right, to have it double the size, the surface area would go times 2, but the volume would go times 3. So this actually doesn't hold as a structure because now you have 3 times the volume to feed by only the double the outer structure to actually negotiate with the nutrients in the environment.
Yeah, so, this is why exactly we don't have like giant insects anymore, right?
Yeah, exactly.
The concentration of oxygen in the atmosphere isn't high enough to support the amount that they can actually take in. You need something like lungs to be able to take in enough oxygen. Exactly. He actually has the example of lungs as well in here.
Exactly, and the lungs are a great example of the solution. Why are fractal structures appearing as an optimization process? Because imagine if your lung was like this, right? And it's this surface area here that intakes, like exchanges oxygen, like takes it from blood and so on. You would have to scale up the whole size of the lung to actually increase the area that is taking the oxygen out. what he describes actually as a solution to this problem is a structure of invagination, right? Invagination is a fractal structure like this. It's kind of one type of space filling curve, right? So just by doing this and then creating dents like this and then creating dents in the dents and dents in the dents and so on and so forth, you start kind of filling, increasing the area, the surface area that is in contact with the environment without increasing the volume by the same proportion or by a higher rate, right? So I think the underlying idea is that you can actually increase in scale by taking that in terms of size and the need of energy intake, for example, by acquiring further fractal properties, because they allow you to behave as if, right, a space filling curve actually fills up every point in 2 dimensions, but it doesn't have 2 dimensions exactly, it has a bit less than 2 dimensions, right? So it's kind of like you can add a dimension to a structure without really adding it fully. So one thing that I started thinking about, I don't think we have time to go into it, but is that we can actually start, sorry, I think this is one of the last stuff, but you can actually start talking about, right, we have today this sort of TA principle, a TB principle, and a TC. We're taking them as givens, right? We're starting them as transcendental logics. But we could try to come up with a theory of how they develop from a same structure by talking about how the size of a society creates an optimization problem, right? And let's say there is a logistical limit to reciprocal relations that is solved by almost adding a new relation. I don't know if you guys remember the Karatani presentation, right? I suggested that reciprocity is kind of requires 2 terms to be defined. Contracts require 3 terms, and commodity require 4. It's like you added 1 dimension to each, right? So you can imagine that a certain structure of reciprocal relations can function by fractal properties as if it had a 3rd one. And a certain structure of contract relations can function as if it had a 4th one, right? So you can facilitate the discussion of how you move from one to another, perhaps by considering how you can actually deform these structures in weird, unconventional ways through this weird resolution changes. And this actually gets synthesized as if you had added dimension a bit in the way that you have like these space filling curves and this optimization issues. But I mean, just showing like interesting places we could develop.
Yeah, just one final thing on these like space filling curves and things. This ratio of the way that the area scales, or the area that the cover scales, is exactly what the definition of the fractal dimension is. So the fractal dimension of constant dimension things, right? If something's 1 dimension, it scales. If you scale it, it scales by the same factor. If it's 2 dimension, it scales by a square. If it's 3 dimension, it scales by a cube. But fractal lets you kind of get in between. So that's how it hacks these optimization problems by allowing you to get closer to something 3D while still being in the 2D world, for example.
So I think that it is a very profound connection between economics and fractals, not at the level of metaphors, but at the level of optimization problems are economic problems of having some finite means and some scalar problem, right? Or some size issue. And you can see fractals being a very common solution to adding an energy constraint, transformations under an energy constraint, right? We added this crazy slide just because I think this is the big kind of, I wrote this just for Dennis, really, to see if he would get kind of,
that's crazy.
Yeah, no, just to see if he would get enticed to look into this. Because what we did today is pretty much talk about this move, right? The suspension of this differential hypothesis leads from differential geometry to fractal geometry. But we know from our topos logic of world things that there is a very important relation between spaces and logic, right? So it would be interesting to ask, what is the categorical treatment of real analysis and differential geometry? In which way this suspension corresponds to the suspension of some restriction on the compositional level. It's something we were talking about just now with this pre-sheaves and what are the sheaping conditions, how this relate, but not specifically with, right? I mean, we should add even to the point here below, right? That this is relativity and quantum, and then you have scale relativity here, right? We're not talking about this. We're moving just to the mathematics. And there is a difference in the mathematics that has to do with this suspension. But how do we interpret this suspension categorically from the compositional point of view, right? What is the say, how do we interpret, for example, limits, convergence, tangent spaces compositionally, so that we can talk about what this means to generalize this, right? This should be equivalent to the categorical interpretation of resolutions and scale spaces, right? To understand this and then be able to kind of reinterpret this move here, right? This should be the equivalent to doing this. So once we do this, we'll have, since these two things are connected, right? The spatial and the logical for us, we'll have a better grasp of what is the logic, or let's say, what is a convergent logic, right? What is the sort of logical interpretation of what it means for all slices of resolutions to converge? And what is the scalar logic, right? And what is the conceptual distinction between the two? Between the space where predicates that are partitioning these spaces, they don't really converge back to always the same limit or the same tangent space, right? So I think that this is just a strategy for research that actually I should have added here these 2 points like this, the actual physics, right? Mm-hmm. But regardless if Nottale's project holds, right? Regardless of if his physical hypothesis here holds, and scale relativity, and here you have relativity and quantum. Regardless of this red arrow, if it works, still he brought to our attention this connection, and it raises by itself, even if the theory in physics doesn't hold, the possibility of making these jumps, right? And I think that this is where we want to get at, right?
This is really the main point I think we were trying to get at, right?
Yeah.
Is what can we take out of this? We're separate from the physics itself, as interesting as it is, right?
Yeah, and I think that this is also a way to respect the physics and not try to say that worlds are scalar like quantum, whatever. That's not really the point. But I think that the core from this is how fractal geometry has resolutions built into it, and that bringing resolutions up should have some compositional interpretation, right? What is it that we're letting go as a restriction when we move from a sort of differential composition to a fractal composition? Yeah. And what would this do for our logical descriptions, right? And our understanding of the logic of different worlds?
Yeah, it's a crazy, dense question, but very interesting.
Yes, I hope you find it interesting so you can help me. But
yeah, we can have another few 4-hour meetings on it.
Yeah, we can have a couple like
just a couple more.
Just on that one slide.
I just added this here because Nottale, very early on, he actually worked on connecting fractals to non-standard analysis and like set theory. So and ultrafilters. So the first attempt he made at defining resolutions was actually based on ultrafilters and the fact that in non-standard analysis you can always divide whatever kind of filter you do into the standard part of that little blob, right? And the non-standard one, and how you would use this to define fractals. And so I just added this because I think it's an old clue that he used to define the theory, but it might be a shortcut because like filters and set theory is already closer to where we are right now, right?
Yeah, this when I read through this gave me the feeling of almost taking the Planck length really like as this infinite quantity where you're sort of gluing together all of these things that are like fuzzy at this Planck length. That's at least how I was interpreting
it.
it.
That's how I understood
in the way of like, I mean, because in non-standard analysis, I mean, the idea is you take these infinite sequences of real numbers and you say that they're equivalent if they agree on certain infinite sets of them that you choose. So I think these infinite sets could be the fuzzy sets of the Planck length.
Yeah, so I think that it might be a good kind of stepping stone to move from non-differential geometries to something that is closer to our pose set and weird filters discussion, right? These are two quotes from Badiou books. This is from Logics of Worlds, right? Where he puts Laurent Nottale as a clear, already relevant, like he suggests that he's taking a lesson from him in the very definition of worlds, right?
He also puts him at the level of Galileo and Einstein, which I think is pretty ballsy.
Pretty ballsy, but at the same time, I think that the word here is this. I don't think it's for anything, that the phenomenon integrates into its phenomenality the variations. I mean, there is a differential language here, right? In this kind of relative description, right? That differentiations are local, right? A phenomenon that integrates into its phenomenality the variations that constitute it over time, as well as differences of scale that stratify its space. But again, within a world, right?
Yeah, it's almost like every world supposes a gluing principle that together these extra structures at every scale, right?
Yeah.
And then novelty, I mean, this really kind of connects everything back to the weak points, strong points discussion of novelty. Just means like, are there things left out of this gluing principle for a given world? And the stuff that's left out, does that, how much of that do we need to indicate another gluing principle?
Yeah, because the whole problem is that you can actually have things that are small or left out, but they are glued back through some weird strategy to the same converging description, right? So it's not enough to have new analytics, like new names. You need to have new names, new syntactic powers, and they both need to be projectable back to the world materially, right? To have something new.
Yeah.
But
in the case of physics, I was going to say, in the case of physics, like it has to respect causality on some level. So that's where, talking about ideal points or kind of points below the Planck length, that doesn't really count as a gluing principle because it doesn't actually connect to the causal structure of.
But I think even the causal structure would still mean something theoretical if you didn't have the experimental counterpart, right? So experimental verification, I think, is what connects it back to the actual parts of the material world, and not that theory describes it as coherent with causality, because it could be coherent with causality and have no experimental counterpart, right?
Okay, yeah. So it's even more concrete than.
Yeah, I think it's even more concrete than that. But I think this last quote here, this is the really crazy one, right? This is from an interview on a really weird text called The Rational Core of Hegel's Dialectic that Badiou wrote in the 70s. And at the end of it, there's an interview with him, a recent interview, which asks about contingency and nature and so on. So, of course, through the work of Meillassoux, contingency became a central question. His way of approaching the question is different from yours. How do you think that this way of treating concept of contingency, right? Meillassoux concept of the necessity of contingency. Is there a finally theoretical relation between something out of place in Badiou's concept, something like in our case would be like below a site, and the absolutization of contingency developed under the concept of the archifossil? And I think his answer is amazing. Like, it's very weird. So contingency for Meillassoux is first of all with respect to the law of nature. But for me, there is no nature and thus no law relating to it. There is an infinite multiplicity of worlds that the transcendental and their respective laws does not cover. This is the same reason why inframolecular universe is not made up of the same laws as the supramolecular universe. there's only interesting path. The only interesting path here is the integration in physics of these differences in scope. We should admit that the scope of a phenomenon, thus the transcendental of a world where it appears, is an immanent given of scientific rationalization. Fractal geometry permits the formalization of this point. So for him, fractal geometry is actually, let's say, conceptualizing how the transcendental of a world is immanently given together with the scientific approach to it. So after which we can let go of a uniform concept of a universe such as that of the nature and of the laws of nature. This project is being brought to fruition by Laurent Nottale. In this context, the question of knowing if the laws of nature are necessary or contingent loses its meaning. So it's weird how he interprets Nottale's. For him, letting go of differentiability means that there is no basic nature. There is no sense of talking about simple nature, out of which complex nature is made up. Mm-hmm. So what you do get is a sort of multiplication of worlds. And the very theory we want from physics is one that accounts for how we're shifting. I mean, very much like what Wilson was saying, right? What is the proper transcendental description at which level? And that differentiation should be included in the theory itself, mm-hmm. right? So Caron is more attuned to this problem with like the whole discussion of multinaturalism. This quote pretty much binds together multinaturalism and transcendental realism. Like, yeah, you have multiple natures. Of course you have multiple natures because you have multiple scales in the world. There are multiple natures. There's no one nature. But this is actually exactly how scientific experimentation works. So mm-hmm. fractal geometry actually would be the formalization of why there is no one nature, right?
Although I think that multinaturalism, as we use it here in Brazil, it's more tethered to, the horizontal translations of perspective than vertical focusing, changes in zooming or something like that.
Yeah, but I mean, I think that this is also the point, right? Do you really want to call changes in resolution vertical when they're not really measurable in terms of going from the complex to the simple? Like, it's true, it is zooming in the extensional sense.
It is zooming in. I mean, but it's fundamentally different from multinaturalism and, the Viveiro sense, this kind of thing, right?
Yeah, but it's interesting that there is an actual good interpretation of it inside of this frame, and I mean, we started from multiple perspectives with Galileo, in fact, right? And we end up with multinaturalism on the other side, weirdly enough. I just added this, but I don't think we need to quote it. It's just that I think that a lot of stuff becomes clear when you read parts of the chapter on relations and the sort of size of the world in Badiou. When you have this sort of idea of, as you go to the top resolutions or the bottom resolutions, they function like points at infinity. Mm-hmm. So it can be both closed and infinite, right? For certain operations. But you could come up with operations that actually move out of the world space, right? And I think that the way that he describes this paragraph, which I think we read together a couple of times in the group, mm-hmm. actually reads very differently when you have all this stuff in the background, and you know that he's also talking about these things, right? So the question of knowing in what sense these things ontologically of the same world comes down to examining for which constructions of multiplicity a world is closed. So constructions of multiplicity and closure actually has to do with, right, the scale measurement for certain operational spaces, and that mm-hmm. it gives you a complete picture, right?
It is like resolution ranges.
Exactly. So it is clear that the mathematical examination of an operational closure concerns its dimension, the dimension of the set within which one operates. If you apply to a multiple a very powerful operation, and if the world is very small, it is quite likely that the result of the operation would overstep the world. So operations can actually lie in a continuum, and the worlds are discrete. So you can move from a weaker to a stronger operation, and that takes you outside of that world, right? So if you place yourself in the Quebec world, and the operation is representing the layout of the city of Montreal in 200 million years, there is a good chance that we'll exceed the resources of the world. Since everything suggests that on this time scale, there will be no city of Montreal, no Quebec, no Canada, and not even a human species, at least the way we know it. The properly ontological examination of the question of the limits of our world presupposes that it is possible to put forward hypotheses on the number of multiplicity containing that world, and that this may be done for the moment in a manner entirely independent from the actual appearing of these multiples, and thus from the identity function which articulates them onto the transcendental of the world. So the ontological examination requires that there is, let's say, a world relative theory, a theory of world relativity, which is what logics of worlds try to be, right? But at the same time, these hypotheses cannot, strictly speaking, be formulated from the interior of a world, which are discretely separated, right? This is what accounts for the fact that the closure in question remains inaccessible. So we didn't really go into detail of this, but we had something prepared that the way that he defines this sort of inaccessible cardinal that functions as the limits for the dissemination and totalization of a world actually give it that same sort of scale relative, but with a kind of type of totalization and a type of dissemination that functions like a point at infinity, right? It has a structure of an inaccessible cardinal. And from inside the world, you can't really pose the question of the outside. Like it has limited resources, right?
Yeah. And here the inaccessible one is very often like the minimum of another world or something. Yeah.
Yeah.
I mean, not necessarily always in scale relativity, but
yeah,
it's a little different. But
yeah, I mean, anyway, I think we already went very, very far into the night, but
yeah, almost 4 hours. I will say, even though I promised not to have any Julia sets, there are some behind me actually on my jacket that Anna made for me. So that's my bad.
No, but I think we managed to talk about fractals without showing any Julia sets, like, and asking people to be in awe of the images. So that was a big victory in itself, I think.
Even though I love them.
Yeah, they're amazing.
They're amazing. But yeah, this presentation was very helpful, and I think it connected everything that we've been talking about.
Yeah, I think that at some point it would be nice, let's say, later in the game, to try to work out some like finer details of some of the properties, because it's clearly something that has, you know, productive kind of insights for us. So, I mean, I think that for our purpose here, getting a feel for why like the differentiability hypothesis being suspended and like having structures that are all scales, this weird relation between continuity and discontinuity, and all these nice resonances with our compositional approach, I think that's already enough. But
yeah,
there's
I think there's enough threads already at the end that we'll be grasping on in many other
I agree
meetings as well.
Anyway, guys,
thank you.
Yeah, thanks.
Thank you so much also, man. I learned a lot from talking to you over this couple of weeks.
Yes.
Really, really helpful.
Yeah, me too. It was good. All right.
Good, guys.
Thanks, guys.
And Caron, next
good meeting.
week, you and Pedro are presenting, right?
Yeah, we're doing the Wilson presentation.
I think it's a really good timing. Like it will be very.
Yeah, everything seems to follow each other. We didn't plan it.
Yeah. A lot what we said today will be repeated from a slightly different point of view.
Perfect.
Yeah, no, that's good.
Okay, guys.
Good night, guys.
Sleep well. Bye-bye.